Welcome everyone. Let's see if it works. GM. Okay, we are live. Perfect. And also some news. Let's go. So what is this here? Okay. Seems it's working. GM properly. There we go. Check this new feature. The highlight. Is here. Can you hear me? Alien, let's go. I love this feature. This took me like 4 hours, and Julia helped me. Finally, we have it. We have it both for YouTube and Twitch. So another step to the pro live streaming. Nice. There you want to enjoy this Ethereum developer bootcamp by Alchemy. Nice. There was a night bot. Wow. I have also the Blu-ray sunglasses. Blu-ray, not Blu-ray, blue lights. Blu-ray, so I don't think. Just 1 second. Don't leave. Wait. Okay, let's start. Really want to enjoy. Finally. Thank you, Kupali. Thank you for your support. I really appreciate it. Yeah, thank you, Alvaro. This is a blue light glasses. They are not graduated. Okay, let's make a giveaway at the end of the live stream. Let's make a giveaway. So I should put the rules somewhere. Where? Nice, Alvaro. Okay, so let me open a Google Doc. Thank you. I will stay hydrated with my Docker bottle. So let me put this here, giveaway. Okay, at the end of the live stream, so 1 share live streams. Nice. Share live stream. Nice. GM. 1 share live stream. 1 tag. You can win. Nice. They're super cheap. You can win a Udemy course. Okay, let's try. I never tried the giveaway during the challenge. So this is the giveaway. Share this link with a screenshot or however you want. What is this? Tag me. The reason why I ask you to tag me so I can see. And at the end of the live stream, I'll select some a winner, at least one, but depending on how the live stream goes, I can also increase the number of Udemy courses, depending on how the live stream goes, but at least one. Let's go. Let's highlight this. Oh, nice. Amazing, amazing. Okay, let's start. We can start. Let me share this. We are close to Christmas, so let's go. Radumna. Let's get it out today. Let's share. Please leave a like, support these initiatives. We are close to Christmas to have a chance to win a Udemy course. Share the live stream link below. Oh, I never tagged myself on this. Be sure to follow me or open so I can contact you. You have no idea how many times I sometimes want to give away and I couldn't contact them. You have no idea. It happened like 10 times, 20 times. Let's start. Center from stream. This is no, I never used the StreamYard in this challenge. Okay. Let's go. So, let's start. And oh, finally we have this. Maybe I should try to make some tutorials. So, let's go. So, I was missing a couple, one or two JavaScript part, but I really wanted to code Ethereum today, so I made them offline, so we can just start with the Ethereum Developer Bootcamp. And we can go. Let's go. It looks good. It requires a lot of time. Yes. And I think it's not perfect yet. Okay, nice. 7 weeks to complete. Okay. Okay, let's start. By the way, now if you are a member, you can use this one. You can use the Francesco's emojis, and I think even if you are not a member, you can do this. I don't know how. Something with TV, better TV, something like that. I don't know. Okay, let's start. So, welcome to the Ethereum Developer Bootcamp. We are so excited to finally release this long-awaited content to the world. This bootcamp used to be worth 3,000 per person, maybe a bit bigger to be better. Maybe like that. You have this. I don't know how you do this, but it's cool. We are so excited to finally release. Okay, let's start again. Alchemy and Chainshot team up to make this bootcamp completely free in an effort to further boost the Web3 developer ecosystem. Nice. The Ethereum Developer Bootcamp has taught hundreds of developers across the world how to build smart contracts and dApps on Ethereum. We are so excited to see you build the next Facebook and Microsoft. Okay? Best practices to maximize the value of Bootcamp. Here's a quick list of recommendations to maximize your AU, which stands for Alchemy University, but it's also the symbol of gold. Student experience. Community. We are not expecting to take all this content alone. So this is why I do this on a live stream. Get involved, be active, reach out if you need help, find your niche, find like-minded folks, wake up at 4 AM, no. Then build cool shit. Can I say shit in my stream? Let's see. Shit. Let's see if this gets some. I got this live stream now. Then build cool shit with them. This is the way. Yeah. The best way to learn is by teaching. Okay. I think I am in the right place. If you see others who are stuck, help them out. This will not only get you street cred. What is a street cred? Street cred. With the AU community, but also will help you solidify because it's solidify. No, it's not funny. Your own understanding of this concept. Show us what you got. Make sure to join the AU Discord. I did it. Choose your own pace. AU is releasing most of its content for asynchronous learning, meaning the course is completed at the pace that you choose. Did I convince you? However, AU instructors will be hosting weekly town halls and community get-together in the AU Discord, which will follow a 7-week structure. So there is 7-week structure. Okay. And as you can see, they are not all available. So we have just 3 available. And the last one will be available on the 12th of January. So let's see. Learn you. Okay, wait. Okay, 7 week. So they release every week. Okay, nice. You get out what you put in. Many folks ask us what is to be expected once they actually complete the content. The truth is, it really depends on the student. Generally, those that invest time for true learning and community networking get out 2x to 10x. I don't know how they decided this, but okay. Learn. Be excited to learn. Go into rabbit holes. Adopt the student mindset. Read and research. Yeah, it's Killian. It's a bit loud. Just lower it a bit. How's it? Okay. I think it depends on. It depends. Some people like it loud, some people like it low. I lowered just a bit. Let's see. If you get stuck, that is normal. Okay, perfect. Nice, Killian. Thank you. Boom. Cool. If that is the normal part of the process. Our suggestion whenever you run into any issues is always a set flow. Do your own research. Google around or chatbot GPT around. See if you can find any similar issues to yours and debug that way. Okay. Look at the ideas. Okay. Give us feedback. Okay. Content format. So I think there are some videos here. I don't know if I want to watch them, but let's see. If I'm forced, I'll do it. Because I don't want to watch videos during this kind of live streams. But let's see. Alchemy University is a mix of instructional videos, research articles, guides, tutorials, and coding challenges. The Ethereum Developer Bootcamp is 7 weeks worth of content. Each day covers a new topic, and the intention is for the concept to slowly but surely build up. The content with each day is typically separated into instructor Loom video, article covering the same material, coding challenges, supplemental reading, weekend project. Okay. The instructor videos and articles are meant to be introductions to concept further explored in that modules guide and coding challenges. It's recommended you both watch the videos. I don't know if I want to do it. Let's see. Okay. For coding challenges, you will also be working in the proprietary Alchemy IDE, a fully in-browser experience meant to get you up and running with coding JS, coding JavaScript, Solidity and more without the need for any environment setup. This is a very, very good one. What can I do after the course? You get out what you put in. Some choose to dedicate their new skill to win all the global hackathons. Some use their newly acquired skills to apply to Web3 positions. Some join high impact DAO. Some choose... okay. Yes. I can also highlight the chatbot. You can create a clip, by the way. The sky's the limit. Okay, nice. You almost convinced me. Weekly content breakdown. Okay, let's just read the week one, because this is what I'm interested in now. We first start by covering cryptography fundamentals. What are hash functions? What makes them special? Hexagon, how's it going? How's it going? Ba -bam, ba -bam, bam. How are they important to blockchains? Then, with the context of having learned cryptographic primitives like hashing, we dive into what makes blockchains work. Consensus mechanism, this one. Basically, how the heck do decentralized networks agree on what is what? Week ends with a project for the weekend, using what you learned over the week to create a secure public-private key server. Okay, let's read also week 2 and week 3, and then we start. Because we have just the first 3 weeks available. I don't think I'll do the 3 of them, but let's see if I can make at least one. Week 2. In this week, we start covering some of the data structures used to make blockchains work. Mainly lots of trees, and the Poon words will be amazing. We also compare the UTXO model that Bitcoin uses to keep track of balances versus Ethereum's account-based model. And week 3, this is the first week where we take a break from the heavy computer science fundamentals and finally start to focus on Ethereum. So, okay, so today we'll still do some fundamentals. It's okay. Let's see. I don't know. I don't think I can do the week 3 too, but this is called Ethereum Bootcamp. So I would like to do this since the beginning. We cover the difference between read and write requests and how these requests are sent to received. Backend responses using the well-known JSON or RPC interface loaded up on the standard Ethereum node. Okay, let's go. Blockchain and crypto. Okay, let's see. Or maybe I can just watch the slides. Maybe we just watch the slides. Let's see what's going on. Let's see if they are not too long. Maybe you can watch it. So, well, blockchain and crypto. Welcome to the Alchemy University Ethereum. Okay, let's go start with this. In this course, we will take you through everything you need to know to build, deploy, test, and interact with programs on the Ethereum blockchain. For the rest of this course, we will refer to these programs as smart contracts, and you will soon see why this term is used. First thing first, let's dive into what purpose blockchains serve and discuss our first core cryptographic primitive, cryptographic hash function. I can't speak today. So let's see, because I think it's boring to watch a video.
Hello, and welcome to Alchemy University's
Can you read?
Ethereum
Can you
Developer
listen?
Bootcamp. Today we're going to be going over blockchains and crypto. First, let's talk about blockchains. So what is the purpose of a blockchain? With a blockchain, we can decentralize where code runs and agree on the output. What this means is that there's no single owner of the code's execution. It doesn't necessarily mean that you can't program rules such that some users have privilege over other users. You certainly can do that as the program's developer. However, what it does mean is that the code once deployed, will always run as programmed. And you can actually go out to the blockchain and independently and transparently verify what that code actually is, right? So if you were to say, hey, at this address, what is the code that lives there? You can go and find it and see for yourself what that code is going to do and know that that code is always going to run that way. That is the guarantee that we get from deploying code to a blockchain. So I ask you this question, take a look at this code in front of us, and I'm curious what your thoughts are on whether this code here is decentralized. The answer is we don't know, right? Because it depends where the code is deployed. It just so happens that the code that I chose to put in front of us is Solidity smart contract code, which is code that we'll talk about later on in the course. However, I could take this code, compile it, and deploy it to my own standalone server that I alone control. In that case, it's not very decentralized, right? I could change this code, I could redeploy, I could take it down. That means that the code isn't guaranteed to tomorrow run exactly the way that it is running today. Blockchains give us that guarantee that code is going to continue to run tomorrow, the next day, the next year, the next decade, the same way that it was yesterday. So when we take this code and we compile it and we deploy it to a decentralized blockchain like Ethereum, that's when we can know for sure that this code is always going to run as programmed. So code decentralization might look a little like this, where you have many machines in a network that are participating in the network, and we take the code and we deploy it out to the network. Each machine is going to have a copy of that code, and when they are called upon to validate or to run a transaction, they're going to run it exactly the way that it was programmed to run. And the blockchain is going to enforce that rule, that they run it exactly the way that the code was written. So a blockchain network would look like this, right? Where you have many nodes inside of a network. Each one of these nodes is a machine participating in the blockchain network, right? The blockchain is the protocol connecting all of these machines, and the blockchain is going to be the thing that is going to enforce the fact that the code is always going to run as written. Since it always runs as written, these programs, this code that is deployed to the blockchain, is commonly referred to as a smart contract. So Bitcoin is the first successful blockchain and cryptocurrency. So this is the one that we're going to focus on when we're talking about blockchain design here in these early first few lessons. There was actually many attempts before Bitcoin, but Bitcoin was the first thing to put all of these cryptographic primitives that we're going to be talking about together in such a way to actually create a blockchain that could continue to work and function for as long as it has today. Many of the components...
I don't know. I think that I'll skip this video. I'm sorry. It's a bit boring. And can you hear me? Yes. Let's go back. I mean, you can watch it by yourself. Okay, -1 for Alchemy University in this case, because I'm looking for a text format. Ah, but wait, this is super nice. Nice. Okay. Blockchains. To understand how blockchain work, let's start off with some high-level question. What is the purpose of blockchain? The purpose of a blockchain is to have a network of computers agree upon a common state of data. Plain and simple. Any person or organization should be able to participate in this process. Generally, the term consensus is used, but can I leave you the slides? Copy link. What if I give you the slides? I don't know if this is legal. I give you the link of the slides. I don't know if I should. I don't know if I did something illegal. Okay. The purpose, okay, any person or organization should be able to participate. No person or organization should be able to control this process. Okay. Generally, the term consensus is used to describe a network coming to an agreement on the state of the data. You will hear this word quite often in regards to blockchain. Shh, don't say this around. So there you have it, the high-level goal of blockchain. Not so bad. Let's explore this further with the most common use case for blockchains, cryptocurrency. On and off topic in today's modern age. Why is blockchain needed for cryptocurrency? To understand why blockchain is needed for digital currencies, let's imagine a naive digital currency without blockchain. Let's make a spreadsheet and give all our friends some money. Like you should give money, no. If you want to help this live stream, just do this giveaway. Share the live stream link, tag Francesco on Twitter. At the end of the live stream, you can win a Udemy course. Let's select at least one winner. It also depends on how the live stream goes. We can increase the prize. Let's see. Okay, Alice, Bob, and Charlie, ABC. Sweet, everyone starts with 10 money. Now Alice wants to buy something from Bob. So she pays him 5 money. Okay. She tells you to transfer 5 more monies over to Bob. So you say 5, 15, 10. Okay. So basically I'm the bank. At this point you might be thinking, there really isn't much to this whole digital currency thing, or more likely, you are considering all the problems with this scenario. Alice, Bob and Charlie need to trust that you won't cheat them. As the bookkeeper, you need to be resistant to bribes. Alice, Bob and Charlie need a way to easily view their balance that is widely available and up to date. Alice, Bob and Charlie invite more friends into your currency circle and quickly the bookkeeping becomes too much for you to handle. Right. We know how to solve problem 2 and 3. Okay. With our programming skills, we can build a website with an awesome UI and an API for making transactions. But what about problem number 1? How do we solve for trust? This was a problem that ate the cryptography enthusiasts for years. Deep down, many self-proclaimed cypherpunks. What is a cypherpunk? Okay. Felt as though the solution was somewhere in the land of cryptographic technology, yet nobody was able to create a foolproof system. In 2000, in 2008, such a system was imagined. A person of persons, under the pseudonym Satoshi Nakamoto, released a white paper for Bitcoin. In this paper, they described a system that would create a peer-to-peer network for exchanging value. This system would combine years of cryptographic research and gain theoretical financial incentives to create a secure, scalable network. The paper describes a chain of blocks tied together cryptographically. This would later be coined the blockchain. Okay. To tie it all together, blockchain was invented to solve for trust. To get a system that's completely neutral and resistant to any censorship or bribe. Cool. Okay, smart contract blockchains. Smart contract blockchains provide developers with a way to decentralize the where the code runs. In this way, code can truly become a public resource. This means code can run without any direct ownership, making it censorship resistant and transparently verifiable. Okay, one important point to drill home is that the decentralization isn't about the code itself, but how the code is executed. For example, let's take a quick glance at some Solidity smart contract code. Okay, cool. Function balances. How long is the video? Which video? This live stream? This live stream is 12 hours. We're just getting started, just 30 minutes. The thing is that every time the thing is that when we do start something, there is this sort of introduction, which can be... Oh, nice. Let me test something here. Okay. It's a bit small. I have to put a dark t-shirt. This look cool. Let's go back. Okay. The quick compile. Okay. The key difference is when you deploy the compile and deploy the smart contracts. Let's go a bit faster. Let's move this. When you do that, the code becomes publicly available on the blockchain. Don't worry, that sounds a bit complicated. Cryptographic hash functions. Before diving any further, you must understand the cryptographic hash function. Okay, let's break this term down a bit. A hash function is just a function. It has nothing to do with crypto by default. So, it takes an input and gives an output. This is a hash function. The thing is that, for example, they give you an output size, a fixed output size. So no matter the input, you will get always the same output size. Not always the same output, of course. You always have the same output size. Another thing about the hash function is that if you with a hash function try to do this with, for example, this string, you will always get the same output. So this is not random. This is basically it's associating like a secret code to an input. Okay, so if I give 52, maybe the day after, I always get the same output, and the output is always the same size. Okay. How do we do that? With a function that transforms this in some ways into this output size. Okay? And there are different algorithms for this. So, okay, so these are the characteristics of a hash function. Deterministic, so the same input, always the same output. Pseudo-random, so it means that it's not easy to guess it, otherwise it doesn't make sense. And then one way, so yeah, if someone gives you a new output, you would not determine an input. Fast to compute, quick to calculate, and very hard to have the same, to have a collision. Okay, let's skip this. There we go. I don't know how you do this, because I have another chat, but is this available on YouTube? Or are you using something, are you using a tool to have this, or? These are the, the members one. Okay. Okay, let's try to using. Okay, now we'll start making something. I want to write some code. Okay, the goal of this challenge is to learn how to create and compare SHA-256 SHA using Ethereum crypto. A library will make quite a bit of use of through this course. So you are here for the emoji. Do you have like better TV? Maybe new update from YouTube, maybe. You should check if this is available for everyone. Hey there, we noticed that you're trying to code lessons on a small size screen. This is a wide screen. Because it's based on the font. This screen is small. I need a bigger screen. I need a bigger screen. This might become a short 34 minutes. I should take notes of this. You can create a clip if you want. You can create a clip of what I did, and then I'll create a short 34 minutes. Okay, So I'll get a bigger screen. To take a picture. Sorry. I'm taking a selfie. Okay. Sorry. Okay. No, time. Let's go. Okay. Can you read? Is it okay? Okay. Brute force hashing. Cryptographic. Okay, now finally we are coding something. Finally. Cryptographic hash function is like SHA-256 are one-way functions. This means that if you have the input, it's relatively trivial to find the output. On the other hand, if you have the output, it's unfeasible to find the input. However, if you knew the hashes of some common inputs, then you could brute force guess at the output to create a rainbow table to determine what the input is. It's easy to find that the SHA-256 of apples is this one. If this was a likely input, a hacker could search for it specifically, and now that the input was apples. Okay. Your goal, find the color. Okay, I think I need some help here. You can assume that all the hashes be generated only from colors provided in the colors array. To take the hash of a color, first use UTF-2 bytes. To translate the string to bytes, then use SHA-256 to hash it. Okay. First of all, let's see if... Okay. Let's see if it works. I mean, not started yet. Okay. 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 So, so we have an array of colors. Okay, so it's just find the color, return the color. Okay, return. Okay, interesting this part. Okay, so we can console A equal we can do the SHA of the hash. Then we can console log it. But this is just a function. Given a hash, return the color that created the... Return the color... Return the color. This is a function. So this is the argument. This. No. Okay. I have to do this. Okay, let's read. First use translate the string to bytes. Okay. Okay, and then let's see. No. What I did? Const bytes. Oh my god. I'm sorry. That's it. Okay. So I take this in input, then I turn this into bytes, and then I do the shove the bytes. So, the respect to string. Okay, but find color as a hash. Return the color that created the hash. Okay. What's the... Okay. Because I have to call it. Okay. So for example, if I do this. I don't know if I should create because this is the array of the colors, okay? Hey Nehemia, how's it going? We're doing hash functions. Okay. To hexa hash. Okay. This is true and this is false. To hex. Okay. So to hex to compare it. Okay. Find the color import that will generate a hash. Okay. The string to bytes. Let's try this. Let's try this. Here, let's say console log A. Okay. To equal red. Okay. Hash is an object. Yeah, I'm just testing here. So hash is an object. So I get the color. So what's the process here? Take the hash of a color. Hash of a color. Take the hash of a color. First use this to translate the string to byte. String to byte, and this is okay. Then okay, you use this to hash. When you want to compare two hashes, so okay, so I take a string, I use it at UTF-8 to bytes, and then I use the SHA-256 to the bytes. Makes sense. And then let's like to log this. Let's like to log this. Feel free to help here. What happened here? I think I need another parenthesis. They're missing a parenthesis. Ah no, here. Okay. True. Okay. Oh, no, but here. Okay. Maybe I need to compare this with this. Still not color. So this is B. Hey Saurab. A B. Let's see. I'm doing well. No, I have to use this another color. This is bad. B. No. Color bytes. Oh, this is bad. False. No. Yes. 2x a hash. 2x a hash. Let's try. It's true. I spelled unidentified to equal red. Unidentified? Should put okay. So the AX. So instead of the let's see here. Rainbow table is simply a table which maps a common input to the hash output. Okay. Okay. Return the correct one, but I don't think I have to. Return the color that creates the hash. Okay. So. Okay, so for example, if I return hash, which is this one, it should go well for the first one. No. Not the hash. Return the color that creates the hash. For array lines. Because, okay, so here we have two colors. Okay, here is trying the hash and it's true for this one. So we don't need this. We don't need this. Okay, so this should be okay. So this part I think is correct because here we are turning it into the UTF-8 and then we do the SHA of this. So this is correct. We check it. In this case, it's true, and we return. But we need to return. So let's do this. Console.log. Let's log this. I think I should return the 2x. No. Okay. If I log this. Okay. So I should return the color. So okay. Colors. So for example here, if I return, so he wants a color that the, okay, so for example if I do this, it should work for the first time. Okay, so and it should return a color. Okay, so this is okay. So let's find, because he wants the color. Okay. Okay. So I don't know if I should use a map of that. So for example, we can use I think maybe just a 4 or for each. So we have colors, for each. And so for each one, for this for example, we can do okay. So for this, let's see. We can even just do a 4. Let's do a 4. Okay. Let's do this. If I do this. Okay. Here we can do colors. Yeah. Okay. Well. Yes, I have to iterate because I want to return a color. And so, and for each color, I should try to hash it and return the one that is the same. Okay. Okay. Const L. So let's check this one. And now, okay. So let's declare this, and then if is the same, if okay. So here we can remove this one, so not this one, so we need this. And then if this is equal to this one, if then we can do this. This one. Let's try. Okay. Let's do it. Okay, let's see. I think I miss... sometimes this IDE throws error. Okay. So... So we have this one, which is cycling through all of them. Should work for green. You won't call. Okay. I should return it. Okay. And I should return the color. Okay. So let's see. Nice one. Public key cryptography. I'm gonna skip the video, but I'm gonna drop you the slides. I don't know if I can do this. Cryptography historically. It's helpful to take a look back as the study of cryptography over the years to understand where and when digital signatures came into play. Historically, up until the 90s, cryptography was the study of encrypting messages so that they could not be decrypted even if intercepted. Cryptography was used for passing important secrets, especially within the military. The sender would take the message and pass it through a function to create an encrypted output. This could be something as simple as moving each character in a string down. For instance, ABC becomes BCD. Okay. As cryptography advanced over the years, more complex functions were introduced to hide messages better. One important leap forward was the idea of a secret key. If two parties can meet prior to their exchange of message upon a particular key, the key plus a function could be used together to create a more secure encryption. Okay. As mentioned above, the state-of-art of cryptography had been increasingly complex version of symmetric key cryptography. The objective of the game was to never let your adversary have your key. Okay. With the advent of personal computing, so cryptographers start to think outside of the box. People would want to be able to communicate with each other securely without having to worry about the eavesdroppers. Okay. So this is the concept of public key, okay. Established cryptographers dismiss the idea out of hand. Yeah, so here we basically they are going through the concept of a public key and private key. Exactly, so you have basically a key which is private and a key which is public. And you can use this public key to interact with other people, like an IBAN, for example, of a bank. Exactly. Okay, let's read this. Now imagine Bob has declared a public key far and wide as the key that identifies him. Bob will keep a private key that corresponds to his public key. When he uses his private key to encrypt a message, he can share it publicly to be decrypted using his public key. Upon decrypting this message, we can say beyond the shadow of a doubt that only Bob could have written this message. The only key that could have encrypted the message is the corresponding private key only Bob has access to. Makes sense. Exactly, it's basically like a digital signature. On the flip side, what if a message was encrypted using Bob's public key? Doesn't make sense encrypting with a public key. Almost anyone can do this since Bob's public key is available. But only Bob can decrypt the message. Exactly. You could rest assured. Okay. This way. Okay. I didn't know about this thing. As opposed to the encryption techniques mentioned in the above section, public key cryptography is considered asymmetric encryption, and the only party has access to the private key. Today, both RSA and ECDSA are two popularly used algorithms for public key cryptography. Okay. The RSA algorithm is based on the idea that it's very easy to find the product of two prime numbers, yet extremely difficult to factor out those two prime numbers. Okay. The ECDSA uses elliptic curves. Okay, let's go. Let's make an exercise. Let's learn public key cryptography by applying it. In this series of exercises, we'll be focused on public key cryptography with ECDSA, elliptic curve digital signature algorithm. Okay, the specific algorithm we will use in SecP256 key 1. Why I can't see the Nightbot comment? What do you think? What do you mean? What do you mean you can see the Nightbot comment on YouTube? Okay. Is the curve used for both Bitcoin and Ethereum. This set of code exercises will be instrumental towards understanding how we can use public key cryptography through the rest of the course. We will learn how to sign a hashed message, recover the public key from the signature, and transform the public key into the user's Ethereum address. This concept will help us understand how the blockchain protocol works and provide us with the tool to use digital signature authentication. We need to prove a user's intention. This will be crucial, this will be cool. Let's jump in. How many did we do? Ah, we already did the 40%. Okay. Okay. The first step in ECDSA is to hash the message before applying the signature algorithm. So if you wanted to sign a message with one your key pair saying that you vote yes on proposal 327, the first step will be to hash this message. Turn this into an array of bytes, the expected format for the hash algorithm. Cost bytes. Yes, it will be. Yeah, of course. Okay, so UTF-8 2 bytes and then CAC 256. Your goal, hash the message. The Ethereum cryptography library provides us with all the cryptography we are going to need. Let's make use of the KICAC. I don't know how to pronounce this in English. Your first step is to take the string message present and turn it into an array of UTF-8 bytes. You can do so. Okay. Okay, this should be not super hard. So we can copy this. So we take this message, we turn this message to UTF-8 to bytes. I don't know, I don't have any idea. I should check it. If you know the pronunciation, put this in the chat. Ask this to Salty. and then return hash. It should be, let's see if it works, and then I'll explain. Okay, so we take this message in input, then we turn this message into bytes, an array of bytes, an array of UTF-8. So for example, let's do this, console.log message. Then I want to, let's break the process. So message, and then we can console.log, and then this is bytes. And bytes, and then we can do okay, let's see, let's log them. It's not logging the hash. Okay, yes. So we have the message, we turn it into bytes. So for example, here they are testing with a hello world. Only with hello world. Okay. I want to see if I can just do this in one line. I think I can. I don't know if it has to be stored into a variable or not. No, it's okay. So I can just do this. Cool. I think it's easier to understand. What do you think? Let's go. Okay, yeah. Okay. Signing the hash. It's time to sign a message using our private key to prove our intention. When sending a message with a SIG-P256K1, okay, we can return a signature along with the recovery bit, allowing us to recover the public key from the signature. This will allow a blockchain node, but we should make a break. Let's do this one and then I'll take a break. Okay. Your goal, sign a message. First step is to hash it using the hash message function. We have this here. Okay. Okay, sign an optional third parameter. Use the same method. Private key. Let's see if we have. We don't have an example. Okay. Is to hash it. So hash message. I don't know if I can. Should put this here. Let's see. Okay. I think I should use this message. Okay, so first step is to hash it using hash message function. This and then. What is this thing? How can I use it? Like sign? Just sign? secp dot sign. Importing. Like this, No. No, but I have to use this private key somewhere for sure, along with the constant private key. Okay, let's read it. Message. Like this. Okay. So I have this is something like that. Private key. No. Length of undefined. Okay. Maybe I should put this. Because here I am. No. Cost hash message equal require. Okay, let's log the message. Okay, so the message is hello world. But we don't. Okay. So as message is this function that returns this. If I do this, try passing the private key and then sing. But the signature here, hash and private key. No, first the hash and then the private key. No, I think I'm missing something here. Here, console.log. Okay. Are we returning this? Okay, we are returning this. Okay, what am I missing? We're very close. So okay, so this is working. Maybe it's just sign. No, sign is not defined because we have sick p. It's just use the sign method. So SIGP is the Ethereum cryptography. Check. Okay. The problem is here. SIGP. This should have a method called sign. Maybe I should return it. No. I should return both. Okay, so recovery bit. Okay. I have to use it to return the recovered bit. Return the okay, so I need to use the last one, which is recovery public key. Sign message as per key options. What is the recovery bit? I think we are very close. Like this, but I need to... No, I need to return. Okay, let's log it. We need to return a parameter. Okay. Okay. Let's log it. It's a promise. So it's a wait. This is an asynchronous function. Okay. Oh, what I did here? Okay. Wait. Okay. Let's log the what I want to return. Console.log turret. Okay. So we just saw this is working. We just need turbot a signal and a recovery bit. Okay. Method takes an optional third parameter called options. She will see in the documentation. This parameter to return the recovered bit. But how do I generate the important point message. I need to read the documentation. Or we can try to ask chatbot. Recovered boolean. Ah, true. No. To return bot a signature and a recovery bit. It says recovered boolean. Okay, let's ask a chat GPT. Let's see. So which is this one? I should have done the okay, so let's ask it. Ask him. Sign method. Checking the GitHub page. Yes, I have the GitHub page. Private key, public key, demo run, function, sign, message, private key options. Okay. There are 90 sign. Let's try recover. Recovery. Okay. Message hash. Okay. Message signature recovery. But this is a recovery. No, this is something else. I don't know. Okay. Sign private key. Once you have the message hash, I have the message hash. This is the message hash. So this is the message hash. Then I pass the private key, but this recovery bit. Click here. Okay. But this is okay. Okay. This is okay, but we can return a signature along with the recovery bit. Okay. Use the sign method for Ethereum cryptography. I think we're very close. We just need to put something working here. Here. The sign method takes an optional third parameter called options, which you will see in the documentation. Oh my god, let's put the right link. Recover it. I like this. No. Recover it, but no. Wait, what is this? Recover it true. So it should be like that. No, here I should put a parameter. Wait, what's going on here? Recover true, but let's cheat just a bit. Two hex recovered. What do you mean recovered true? As a parameter? Wait. Signature recovery bit. Expect the recovery bit to be a number. I choose this number. No. So okay, so this is the array, which is the signature. I should return the signature and the so I think this is correct, but here they say the sign method takes an optional third parameter called options, which you will see in documentation. Use this parameter to return the recovered bit so the public key can be recovered from the signature. Recovered. Okay. Ah, like this. Like this. Like this. I think I got it. Done. Recover true as an option. Okay, done. I should have taken the break. So amazing. Break. Be right back. Done. Let's go. Let's go. This is small. Okay. Let's take a screenshot. Okay. Coffee break. Okay, where is the live stream link? Beh, I can just. I'll also retweet soon. Let's see. Coffee break. Let's see here. Okay. It had to be put as an object, of course. So let's go. Okay, next stage. No, big coffee break. Oh. Let's promote a bit this live stream. By the way, yeah, this is what I wanted to do. No. Okay. Let's close this. So share the live stream link. Tag me. At the end of the live stream, you can win all the course. Let's see. Okay. Okay. Let's see. Oh, let's remove this. Let's see how is it going. Next stage. Recover the public key. How is it going? 42%. So public key, first primitive, digital signature. Okay, then proof of work. Okay, and then we have week 1 assignment. CDSA model. Okay. Nice. Let's go. So recover the public key. When the signature. Maybe I should share it a bit more. You can share this. Okay, we're live. I forgot to send the email. Let's do this. I forgot it. A newsletter. Let's see if that giveaway attracts some people. Let's see if we get more people here. The video live stream. This is my level of how lazy I am. Here is how you let's go. Hey Deepan, how's it going? Let's go. Ethereum Bootcamp. Esatto, you can win Udemy course. Let's go. That's it. Okay. Yeah. Nice. Let's see if we get more people. Okay. Schedule the issue. We need more people. Send it. Share and spam it a bit. Let's see if we get more people. Okay. Nice. I think I didn't change the title. Okay. Let's go. Okay, let's go. Okay. One second. Okay. Let's do this on Discord. Let's see if we get more people. Oh, we got 2 more people. Okay. This is the Discord server. For C, cool community for content creators. We are level 3. And yeah, this is the general chat. Let's see. Twitter chat. Let's do it. Let's see if I can. This is the event. Oh, I didn't put the event. This is why. Let's promote me a bit. We need some more people today. Francesco's 12-hour live stream. Today is let's put 9 a.m. until 7 p.m. 7:30. Today is 11th of December. Okay, let's upload the cover. Where is the cover? I can find it. Okay. Oh, there we go. Okay. let's go. Let's create the event. And then we start the event. I always forget to start the event. Okay. Because okay. Maybe we can in the event announcement. Okay. Okay, let's go back. Needed some promotion. Okay. Okay, let's go back. What is this? Let's go. Okay, so recover the public key. When a signature is passed with all of its components, the public key can be recovered. This means that blockchain nodes will be able to understand who's seen the transaction that was sent to them. A transaction could indicate that the users would like to send one Ether to another address and provide a certain transaction fee. Since the signature signs the hash containing this intention, it is enough to authenticate this action entirely. Your goal: recover the key. Given a message, signature, and recovery bit, find the public key and return it. Be sure to hash the message when passing it to the recovery method. Use the noble documentation to find the... Okay, so basically... I don't like this part of the tutorial, to be honest. But let's see. To be honest, for now, I like the Learn Web3 DAO more. But I mean, let's see. Recover the public key. Recover the key. What is this example? Yes, just like just go and do it. No, don't like it. I'm sorry, Alchemy. Recovery key. Okay. Async function, recovery key, message, signature, recovery bit, passing it to the recovery method. Okay, so let's go on the recovery method. What is the recovery method? Recovery key. This one. Okay. Okay. And okay. So the recovery method, recovery key, message, signature, recovery bit. Given a message, signature, and recovery bit, find the public key. Find the public key. Public key is generated by doing scalar multiplication of a base point by a fixed integer to result. The result is another point. What? To get point instance. Okay. I just have to use this. Just have to use the method. Get recover public key. No. Okay, no, wait. Const a equal to await. Okay, console dot. But why do I still have stuff here? Also, something that I don't like about this tutorial is that you can't reset. Like, if it's like you can't reset this. Like, if I delete this, I'm done. I'm doomed. Let's see. Received. Okay. X2 bytes. Okay, so first of all, let's log them. Console.log. Let's log the input. Message. Quindi message signature recovery bit is 0. Ok. Sigp.recover public key. But this is a method. Recover public key. Functional message hash. X2 bytes. Received invalid unpadded X11. What is this? X2 bytes. Message hash. Signature recover. Public key is generated by doing scalar multiplication of a base point by a fixed integer. What? Which we will by default encode to X. This one is this one. Point for signature hash signature recovery. Point is not defined. Okay. Point is not defined. Okay, but we are getting there. Public key is generated, so we need the public key by doing scalar multiplication of a base point by a fixed integer. It says point is not. Ah, no. Recovers. Message, signature, recovery, Wint 8 array, message, signature, recovery bit. Find the public key. What do you mean? X2 bytes. Received invalid unpadded hex 11. I think this is a wait. Hash the message. Hash the message. Hash the message. Which message? This A? No, but let's go on the documentation. So, public key, message hash. We already have the message hash. Recover public key from message hash, signature, and recovery bit. Message hash, signature, recovery number. Public key is generated. Ah no, this is how they do that. So I don't need to. I do this by myself. But I mean. Hex 2 bytes, received invalid unpadded hex 11. We need to hash. Hash the message. Okay. Maybe this. Nice. Amazing. Thank you, Xavon. You are rocking today. Okay. Key to address. Bitcoin and Ethereum both have a transformation process to take the public key and turn it into an address. For Bitcoin, it includes. It's going well, Pradumna. This tutorial is basically just telling me like go to the documentation and do that. So it's I don't know. It's good, but I don't know. Maybe it could have been better. I don't know. Ethereum address transformation is quite a bit simpler. Its address is the last 20 bytes of the hash of the public key. The important thing to recognize here is that the address is differentiated from the public key, but you can always derive the address if you have the public key. Your goal: get Ethereum address. Let's get the Ethereum address from the public key. The first step, you need to take the first byte of the public key. The first byte indicates the format of the key, whatever is compressed. The public key will be a unit array. Okay, you will need to take the first byte of the public key. You can use the slice method. Next the caca, don't take the last. Okay, this is okay, let's try. Okay, so feel free to help because I don't know. Let's see. So first step, so we have the public key. Slice. We can say one and array dot length because I don't know how much is one array dot length. Wint 8. This is the array. So, okay, so. Okay, so take off the first byte. So this is the first thing, and then we can log it. Console.log. So take off the first byte, then use I don't know how to pronounce it. Kekak, Kikak. I don't know. KitKat. Okay. Hash the rest of the public key. So it's Method. I forgot. Of the public key. Should I also do the UTF-8 to bytes? Who knows? Const step 2. This will call it step 1. Okay, step 1, step 2. Okay, step 2, and then we console dot log step 2, and then step 1, step 1. This is step 2, and then step 3. Take the last 20 bytes. The last 20 bytes. Interesting. Const step 3 equal to we have this step 2 dot slice the last 20. So how do I take the last 20th public key length minus 20 public key okay. I don't know what I'm doing, but let's see. Console, then we'll see if I did at least the first. Should I return it? Return step 3. Let's see if I did at least one thing right. No. Okay. Ah, wait. Oh, no, wait. This is already a TF8 array. No. Expect to equal. Okay, it returns something. Wait. It's it's returning something. This is already a good news. Step 2. KitKat hash. It's empty. No. No, this is step 2. Like this. Bam! Done. Genius. So this is the nature of programming. Like 1 hour ago I felt like the worst developer ever, and now boom, I feel the best one. Okay, nice. This is the nature of programming. 9 OM, so it's like cool. Let's go. Let's go next one. Supplementary resource on digital signature. Let's see, DSA, Bitcoin. Okay, I'm skip this. We have good explanation. I'm not gonna read this. Mining and proof of work. Bam! my god, I'm dying. The live is over. Oh my god. Let's try to refresh. No. Let me send a message to Vito. He's probably sleeping. Okay. 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 We are sorry. But it was just this. Okay. It's just a video. Maybe it's Loom. Maybe it's Loom. I thought that all the page was okay. We can still do it. It's funny because we are talking about decentralization and like the service is down. I don't know if it's Alchemy's fault. Nice. Okay. Okay. In a centralized environment, common issues are. How do I know? Let's see. Alchemy is gonna block me. If I post this, Alchemy is gonna block me. Let's do it. I'll post it later. Okay, Alchemy is gonna hit me, I know. But I have to be honest. Even if I love people from Alchemy, I have to be honest. Centralized environment common issues are. How do all nodes agree on what the current and future state of users' account balances and contract interactions is? Who gets to add the new blocks transactions to a chain? How do we know any blocks added are valid? How the heck are all these things coordinated without any central actor in place? The answer is consensus mechanism. Okay, consensus mechanism, coming to general agreement. I'm gonna skip this part. I think it's too... Let's just read this part. Bitcoin being a blockchain network uses a consensus mechanism called proof of work. Ethereum was previously using proof of work, but it has since moved to proof of stake. So this is a sign that this tutorial is up to date. We will not be covering proof of stake here for now. Okay, let's do proof of work. Proof of work, mining is the work itself. Okay, this is a very long explanation. Let's skip it. Let's skip it. Shh, don't say this around. Okay. We're going to build a basic proof of work miner. The miner will receive transactions from the network and add them to its mempool. When a block is ready, the miner will take those transactions. By the way, today I'm using these blue light glasses. Let's see if they block a bit the light and I have less stress on the eyes today. Let's try. Okay. I'm trying to make it a bit bigger. Okay, this is what I can do. Okay. 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 So the mempool. Users who want to make a transaction will broadcast their transactions to the blockchain network. The mempool is a place for miners to keep those transactions before adding them to a block. Typically, the miner will take all the transactions with the highest transactions fees from the mempool. Then they'll add them to the block and attempt to find the proof of work. Okay. You can find more information on Bitcoin miner fee priority. Your goal is to implement the add transaction function, which adds transaction to the mempool. Take the transaction sent to the function and push it on the top on the mempool array. Okay, add transaction. Take the transaction sent to the function. So it's just mempool.push transaction. Why there is a to do here? Okay, another thing that you added to the mempool. Not funny at all. So one thing that I don't like much about this tutorial is that they are like tied together. Like here there is already the to do for the next one. I don't like this part. Savon, today we are laughing like crazy. The goal of this stage is to update the mine function to create a new block with a unique identifier and add it to our blocks array. For the purpose of this mining exercise, our block will be an object with a single property, an ID that is equal to the block height prior to it being mined. Update the mine function to create a new block object with a single property. Blocks. Create a new block object with a single property ID. So I have to create a block object with a single property ID. Set the ID property of the block height. But where is the block, the height? Push the block object. Blocks dot push. So this is the last part. Let block equal block height prior to the new block being added. What does it mean? Block height prior. Set the ID. Let's see if we get the error. Okay. ID1. I don't get this. For the purpose of the block height. ID1. Set the ID property to the block height prior to the new block being added. But this is the first one. No, this has to be height. No, I don't get this. ID property is the block height prior to the new block being added. Block here is just an object with ID. Let's cheat a bit. Let's see if I understand. Blocks length. Length. Di già, the poo. Let's go. Maybe this is blocks dot length. The length. Why couldn't the block by beer? So here they say block height, which is basically the length of the blocks array. Okay. Let's go, Eddie. Let's go. 2 hours already. Let's go. Block hash. Okay, so typically all the information in the header of the block is hashed together to create a unique hash based on those properties. If anything changes in the header, it will affect the hash. Okay, since each block also contains the hash of the block before it, it will affect every future block as well. Okay, makes sense. Your goal, add the hash. Stringify the block object using JSON stringify. Okay, but where? In the function mine? Yeah, it's super tricky. Why? Why do you hate? It's already hard, even if you tell things. Okay, let's go, let's go. Okay. So, JSON stringify. Stringify the object. Just stringify the object. Stringify the block. Block const a. So always let's console log it. Console log a. Take hash of the stringified blocked. The sha. I forgot here how to do this. Set the resulting value. Do not have the hash property on the block. Okay. Let's see. Forget that. Okay. Okay, so this is okay. Should add the blocks. Should return the expected hash. Okay, so we are getting there. So just stringified the object. Okay. So we stringified the object, and now take the hash of the stringified block. Const sha object. I forgot how to do this. SHA-256. No. Let's use ChatGPT. Let's use ChatGPT. Okay. Let's see if it works. Let's see. Oh, I'm cheating. No, Python. I need the JavaScript. Don't judge me. Okay. I'm dying. We have pizza for a while. Oh my god, I'm dying. Create hash. It's not this one. Create hash. It was another function. Let's go back here. So ChatGPT is great for live streams. Nice. Everything which is good for live streams is okay for me. Crypto.js. Yeah. I need an example. Crypto.js. So it's like this. Let's go back here. Bar. Like this. Let's see. So if it works, I'll explain. Let's see. No. You don't find a hash property on the block. A hash property on the block. Have you checked out Codex.js sandbox by OpenAI? No. Or maybe yes, but I can't remember. Did not find a hash property on the block. A hash property. Set the resulting value to a hash property on the mind. A hash property. Okay. Sorry. Block. Sorry. Hash. Can I do this? Block hash equal to this. Because this is a block and the hash of the block. No. Shaho. No. Oh, let's do this. You're right. Thank you, Xaon. Nice. Thank you, Xaon. Thank you so much. Yes, exactly. So we add this on the property. And let's do a console log. Thank you. I appreciate. Block. So this is okay. This is the hash. Cool. Let's go. Mine transaction. In Bitcoin, there is a specific block size limit that cannot be exceeded. The number of transactions that will fit inside of a block varies due... okay. Your goal, mine transactions. So, inside... what is that to do? Inside the mine function, pull transactions of the mempool and include them in the block in an array called transactions. This tutorial is I don't know. It's more like do that, but they're not explaining many things. Yeah. No, Alchemy is amazing. And don't say that sometimes this tutorial, I want to be honest about tutorial, is it's a more like do that. I mean, it's it can be a way, but it's not very beginner friendly. But I mean, we will do it. And some pull transactions of the mempool. What I mean, it's free, so it's nothing to say. Pull transactions of the mempool and include them in the block. I mean, I tried many. Let doesn't have dark mode. That's a boomer. Okay. Should add 2 blocks. Okay. Should add to the blocks. No, blocks. Transactions. Wait. It's for intermediate devs. Yeah, it is. Hey, Madu. So, inside the main function, pull transactions of the mempool and include them in the block. Pull transactions of the mempool, include them in the block in an array called transaction. Okay. So it's like block transaction like this. So it's a property of the block. Let's see. Have you started with Ethereum, Buzz? I started with Ethereum. This is the Ethereum Bootcamp. Okay. Okay, expect 0 to be equal to 5, okay. Excite the transaction. Pull the transactions of the mempool. Pull of mempool. Mempool. Just copying the reference. Okay, so I copy. So I create a list, an array of transactions in the block based on the mempool. Okay. Remove each transaction to include in the block. Before hashing. Okay. Remove each transaction you include in the block. Okay. Pull transactions of the mempool and include them in the block in array called transactions. Remove each transactions you include in the block from the mempool. Remove. We are almost there. So I should remove remove each transaction you include in the block from the mempool. But I just created this transaction from the mempool. Remove each transaction you include in the block. Transaction you include in the block. Okay. I have to remove all the transactions that okay, because the okay, so I have to reduce remove I think I got it. Filter. Yes. Filter. Powerful. So array 1 is basically mempool, and array 2 is so array 1 is mempool, and array 2 is block dot transactions. And then the filtered array is array 1 filter to includes, and then I can say mempool, but I don't know if this is gonna work. No, of course it is a let, sorry. So I have to remove the block transactions from the mempool array, assign to a constant. Const mempool. I think it's like this, just this. Mempool. I just have to do mempool.filter. Mempool.filter. Filter. This. I think this works. Let's see. No. Mempool.filter. Okay, so let's do this. Console.log mempool before mempool 1 and this mempool 2. Let's see if it's filtering. No. Come on. Let's see. I know what I have to do at least. Mempool equal. No. Because it's a constant. If I type let. Let's see if it works. I'm cheating a bit. No. Right. I think I have just to remove. I just have to remove the elements. I have to remove elements from an array given another array. Remove elements from a const. Filter method. But here it says create another array. Okay. Okay, first of all, let's do this. Const new array. First of all, let's see if the new array is empty. Yeah, it's empty. So I have the mempool. I add the mempool transactions to the block transactions property, which is an array. Now I want to remove them from an array. So I have the new array. But if I say like mempool equal to new array, maybe I have to use another array. No, I have just to remove something from the array because the filter works, but you can't do this. I have to use array methods. Remove elements from a constant array. Delete element in array constant. No. Okay. Okay. Yes, I think I have to use splice. Splice start index and number to remove. But I have to splice. JavaScript splice. Let's see an example. We need an example. Very hard. No, not hard, but splice. I can put an array. Thank you. Thank you for subscribing. Thank you, Marvin. Thank you, Marvin. Okay. Cool. So we can splice an array. Maybe we can just splice the array mempool dot splice block transaction. Okay. So no. Okay. Mempool 2. So this is right. Put 0 to equal 5. Should create the mempool, okay? Mempool 1. Sender Bob to Alice. Okay. But this is correct. It's splicing block transactions. So new array, no. Why this is not working? Okay, I think we are getting close. Pull transactions of the mempool, include them in the block in array called transactions. Remove each transaction you include in the block from the mempool. So mempool splice block transactions. Add the transactions array to the block. Wait. Okay, got it. Post. I have to use another one, because otherwise this is this to remove. So first of all, let me see if this works, and then I'll comment. Second. No. Okay, we are getting there. Should store the transaction on the block. Should store the transaction on the block. Okay. Block transaction equal to mempool. Cost remove block transaction. Let me move this. We are getting there. We're just playing with arrays. So we have an array in the block, array of transactions, that we need to add the transactions from the mempool and then remove them from the mempool after adding them to the transaction. So block hash block push. Wait. So the block transaction is no. Wait. No, because here we put the reference. No. Const to add. No. Wait. I don't know, my video keep loading for 5 minutes. Okay. So okay. Okay, I think we have also something to add at the end. Okay. 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 So we have a okay. Block transaction. So we need to append an array. Let's try. Let's try this. Then console.log block transactions. Let's see. Playing with the red. Ooh, the first one was okay. So the first one was okay. We're getting there. The first test has been passed. should. Okay. Okay, so we do this, and then we need to remove maybe also the to remove. So we are getting a copy of the no, three dots. That's it. We're playing with arrays. Okay. Block transaction mempool. But here is to remove. Let's do this. To remove. Okay. I think we don't need this. No, we don't need the filter. Okay, so we splice with the remove. And this is okay. Okay. In the second test, the first is okay. We add the block. We should store the transactions on the block. Expected 15 to be equal to 10. Okay. We just need to add the first 10. Let's try chatbot. Yes. And I mean, it makes sense because I still have to type this concat. Slice. Slice. Maybe we can use the slice 010. Slice 010. Slice 010 to remove. Hey Aldrin, how's it going? There we go. We have also the overlay now. So block transactions to remove is no, it should not be. Can you hear me? Can you hear me? I can hear myself. Are you sure? Yeah. You can hear me, Aldrin? Is it okay? Oh, okay. Yes, so, but we need to add only the first 10. Android issue? I don't know. Maybe his volume. Aldrin's volume. Not mine. ASJ, there we go. So, we need to add only the first 10. So, it's not this. Maybe the splice. Maybe we can do like this. dot splice 010. Let's see. No. What? Are you trolling me? Thank you. Const new okay, then console.log. So let's log this new array. Oof. Okay, new array. Okay, now new array dot splice. New array dot splice 010. What am I doing here? No, array splice. Okay. Let's go here. Let's go on ChatGPT. Get only the first 10 elements. Only the first 10 elements. Slice. Okay. 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 Is it okay? Array slice. Block transaction to slice 010. Ah, okay. Okay. Okay, so we can do this. Const array, and then we can do we can say that block transactions is equal to a new array, this one, to this new array dot splice 010. Let's see. Okay, we got 3. Okay, this works. This is green now. Nice. Should reduce the mempool to 5. Reduce the mempool to 5. Expected 0 to equal 10. Okay, let's remove some stuff here. What is the to remove? Is just the block transaction. Okay. Let's see. Okay. Okay. So let's see what's the problem here. Okay, okay. Okay. But it's reduced. To remove 3. We are very close. We are very close. Should reduce the mempool to 5. Ah, okay. Ah, instead it reduced it. Mempool splice to remove. Okay. Okay, mempool to remove is just block transaction. Okay, we are getting so close. So we have this array. We okay, to remove why is it empty here? Because when I splice, because everything are the same. All of them are the same. So they're elements with the same value. Okay. So mempool splice console log block hash const to remove mempool 1 to remove. So here the mempool is 15 and to remove is 10. To remove is 10. Why? Because to remove is the block transactions. But it makes sense. So why is it if I'm splicing just the elements. Let's see. Oh, done! It was just the element, not the array itself. Nice. Nice, very nice. I'm preparing some posts. Nice. I got the click moment. Thank you for staying with me and struggling with me. So, okay. Alchemy is gonna kill me. Alchemy is gonna kill me. Okay. Alchemy is gonna kill me. I don't care. Let's go. I should take a break. Okay. Let's see how it goes here. Build a miner. Okay. 3 hours. 3 hours, so we made 45% of the whole, no, 60% of the blockchain cryptography in 3 hours. Not bad. I hope this is not very long. In Bitcoin, difficulty is adjusted every 2016 blocks, which is about every 2 weeks, with the blocks being mined on average every 10 minutes. Okay, your goal, proof of work. Now it's time to actually mine the block. This is where we get the work part of proof of work. In the mine function, prior to hashing the block, add a nonce property. This property should start at 0. Keep changing the nonce until you find a hash that is less than the target difficulty. You can compare a big int to another big int using the JavaScript comparison and big over. Okay. Okay. So where should I start? Prior to hashing the block. Ah, it's the same as before. Okay. 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 So prior to hashing the block, so here to do add a nonce property. So blocks.nonce. This property should start at 0. Keep changing the nonce until you find a hash that is less than the target difficulty. Okay. Keep changing the nonce while okay. Keep changing, so I smell a while. Okay. Okay. Consta hash example. Big int. What? You can convert a hash until you find a hash that is less. Keep changing the nonce until you find a hash that is less. That is. Expect the hash to be less than the target difficulty. It is less. It is less. So I don't understand here. Loop and if statement. Loop and if statement. But what? Loop what? Loop. So what's the increment? Okay. No, that's clear. Okay. a hash, keep changing the nonce. So the nonce should start at 0. Keep changing the nonce until you find a hash that is less than the target difficulty. Okay. Ah, okay, here. Ah, okay. I think I got it. I think I got it. So, for example, here, basically we are okay. What is? Okay, so this is, let's put the block hash. What is it? It's an array. Okay. So this is the hash. Okay. Okay. I'm getting there. Const int equal begint of block hash num. Let's log this one. Okay, num. Okay, let's see. Is it live? Yes, it is. Nonce plus plus. No, because it's generating a hash. This is what I said. So it should be like while. Okay, so we generate a little ice stream. Okay, I told you. So yeah, this is what I said. We can't increment. We just generate another hash. Welcome, Tokyo. Hi. I don't know why I can see your profile picture. Ah, no, I can see it. Okay, so we generate the hash. Keep changing the nonce. Changing the nonce. Change the nonce. Increase the nonce. Keep changing it means increasing. It's not clear. So we have this num, which is like, let's compare them. I should see a true or false now somewhere. False. Yes, so this condition should be okay. So this is where we get to work part of proof of work. Is in the main function prior to hashing the block add a nonce property. This property should start at 0. Okay. Keep changing the nonce until you find a hash that is less than the target difficulty. You can compare a big int to another big int using the JavaScript comparison operators. You can convert from a hash to be a big int. Okay. We just need the last one. Should have a hash lower. Hash. Keep changing the hash. Okay. Yeah, but I hope I don't break everything. Now I want to say this. Okay. This was too nothing. Don't say I don't wanna waste the time. Is it different? So if the nonce is 2, should I just increase it? It's no. 2. Okay, it's different. Let me see, 3, 4, 9. I can't read it. This is bigger. No. No, it's the same number. It's the same number. Yeah, because the hash is not based on the nonce. I should base the hash of the nonce. In the main function, prior to hashing the block, add a nonce property. Start at 0. Keep changing the nonce. Changing, what do you mean? Keep changing how? Changing how? Until you find a hash that is less than the target, until you find a hash. So the hash should be based on the nonce, but how should I generate the hash based on the nonce? So maybe we need just a while. And just increase it. So what is the condition? Console log is num is less than the target difficulty. And then the hash. So let's type this while loop. I hope I don't break it in the memory. Block nonce plus plus. So this is the condition, and while it's true, what is the condition? If what is the check? So we have this num is big int, we log, this is num, if num is less, so if it's false, num should be bigger. But num is the hash. Okay. So if it's lower than the target diff, so if it's lower, so if it's greater, then you break, and then let's try. I hope I don't break it. No. Just another parenthesis. Let's see. Nonce. Wait. Nonce. I call it nonce. It's nonce, non nonce. No! I break it. The memory! Wait. I'm not hashing it. Yeah. The hash, yes. Let's remove this, because the hash is basically this. I'm doing an infinite loop. Okay. Block a hash. I think we don't need this. If num is bigger, less. Done. Let's go. Okay, let's go. Let's clean this up a bit. Okay. So, while loop, block hash, num, so we can remove this. Let's clean it up a bit, this one. Okay, let's see if we can do something a bit. Okay, nice. Maybe we can. Let's see if I'm breaking it. No. So, for example, maybe here we can put a nonce 0. Let's go, Marvin. Okay. Hashing and proof of work. Proof of work is another component of Bitcoin that is essential to its success. Let's examine its origin and... okay. Control difficulty. Why should you use proof of work? Saving 1 gram at a time. What's going on? Okay. Okay. So this is a basic of proof of work. So it's okay. Let's skip this one. Further study. Supplemental resources of proof of work. History, Adam, Bitcoin mining pools. Okay, that's cool. Blockchain structure. How is it going here? Close to 69%. Blockchain structure. We finished the blockchain cryptography. Let's see if 69 tweets. Okay. Let's go. Okay, I'm not watching this this video, but we have the slides, and I can. I don't know if that's legal, but I'm gonna show the slides here. Okay. Blockchains are just fancy databases. Architecture is a distributed database of a list of validated blocks. Each block contains data in the form of transactions, and each block is cryptographically tied to its predecessor, producing a chain. Nakamoto. What is this? Blockchain are not just decentralized but also distributed databases. Those it circles mere to be nodes. In computer science, the term node simply means a unit or member of a data structure, a graph. For practically, a node can just be thought of as a computer. So data structures have nodes or computers that you have just updated. Okay. There is no central administrator, say a super node. Okay. Yeah, okay. It is always the same. No, blockchain demo. Okay, this is a cool one. I think maybe this is a good thing to add to the resources. Maybe. So the Genesis block is the first block in the blockchain. The block should have an index of 0. Okay. Each block stores the following information: index, timestamp, hash, previous hash, data, and nodes. index, the position of the block, timestamp, hash, previous hash, data, nonce. Valid hash. A valid hash is a hash that meets certain requirements for the blockchain. In the demo, having 3 zeros at the beginning of the hash is a requirement for a valid hash. Okay. So this is the requirement for having a valid hash. And the number of leading zeros required is the difficulty. Data integrity in a blockchain data structure. If a blockchain is just distributed database, how does the data it's stored? Maybe a bit bigger. Let's see better. I want to make sure the state of the data is never corrupted in any way. The next parts of the demo touch on how difficult is it to manipulate data in a block that already has many blocks mined on top of it. A bit bigger. Okay, since data is an input variable for the hash of each block, changing the data will change that block's hash. The new hash will not have 3 leading zeros, and therefore they become invalid. Okay, nice. Yeah. The first 3 should be zeros. Yes. So basically, you can manipulate your own data, but then the hash will be different. Exactly. Adding a new block. The demo continues with a brief explanation of what it takes. Okay, here he's explaining more like how it works, how does it mean to text a new work, but let's go. Build a blockchain. In this lesson we will build our very own blockchain implementation. Okay. We will learn about blocks, hashes, and how blocks are linked together to create a cryptographically secure blockchain construct. The resulting blockchain implementation will look a little something like this, where each block contains a previous hash representing the contents of its predecessor. Okay, this is interesting. Okay, let's code a blockchain. Cool. Let's go. Okay. I hope this is step by step, but not just do it. Okay, so blocks and hashes. Hashes is aptly named. It is in fact a chain of blocks. Each block contains transactional data, some metadata describing the block, and a link to the previous block. Okay. These components are fed into a hash function. Your goal is to return a hash. In your block.js file, we have a class block using the to7 function from the return a valid hash. For now, there is no need to hash anything in particular. Return a hash. Return a valid hash. Return a hash. Yeah. Just this. So I want to return Xavon. There we go. I hope it works. It worked. New kid on the block. Xavon, if you are still there, you are the new kid on the block. The next stage. Adding data to the hash. Okay, so here now it's going well. I didn't read the thing. Amazing. It's time to add data to our hash. This will ensure that the block's hash is tied to its component. Okay. When creating a new block, data will be passed to its constructor. Let's add a data property to the block. Add a constructor to our block class. That takes one argument. Okay, so we need a constructor here. Constructor data. This data equal to data. Make sense? Let's add a data property. To hash use this data to calculate the block's hash. Okay. Okay. This part is done well. Let's see if I'm doing it well. No. What I'm doing wrong? To hash data. What am I doing wrong? Add a constructor to our block that takes one argument and block. Like this. I have to use the inner property data. Let's go. The Genesis block. I like to watch it sometimes. Thank you. A new file, blockchain.js. How exciting! This stage is going to focus on adding the first block to our new blockchain class. Okay. The blockchain.js file. I like this part. The blockchain.js file contains the blockchain class. Okay. With a chain array. There we go. Let's add the Genesis block to this array. Create a new block in the blockchain constructor and then add it to the chain array. Const Genesis equal new block. Create the Genesis model. Like this. Just calling the constructor in the BAM. Okay, create an add block function. Let's create an add block function on our blockchain. I like this part. Oh my god. Let's go back to the beginning. Oh. Nice. Can you hear the music? Let's create an add block function. Okay. This function should take in a new block and add this to the chain array. This dot chain dot push block like this. This. Bam, done. Why didn't blockchain see the commercial? Because it has add block. After this, break. This is so fake. No, let's make the super serious face. Second. go in full mode. Second. No. No. I can't do it. Wow, Windows. Like this. Not funny at all. Anyway. Next stage. Linking the blocks. Previous hash. It's time to add one more crucial input to our block's hash calculation, the hash of the previous block in the chain. This creates a chain where any change to the data of an ordered block will affect each subsequent block. Your goal, link blocks. Julia! I'm starving. I need food. Okay, if you bring me food, I'll give you a shout out on Twitter. So, okay. Nice. It's going well. Add the previous hash property to each block. Okay, this is very tricky. This previous hash. I'm not gonna... No, I want to copy paste it. At the previous hash property, the value of this property should be the hash. The value of this property No, this is wrong. Oh my god. Okay, I should read everything before start coding. A good spot to add the previous hash property on the block would be in the add block function, where a block is placed on the chain. Okay. No, this was right. No. This was correct. Plus. Okay. The blocks there is a typo here. but not in the constructor. Okay. Okay. When you add the block, okay, when you add the block dot okay. Hash. Second. What is the previous hash of the Genesis block? Let's see here. Let's see. So we have the last block. So the previous health should be so this one. We get the chain. We need the so there should be to hash. Ah, okay. To hash. Let's try to. Okay. Let's try to log the console.log this chain. No, not here. The previous. So like this. Because the chain is increasing the length every time. So if I log it 0 1, okay. Okay. So this is 1. And if I log this chain is an array of blocks. This chain. Ah, I can try. So this is the index. Okay, so this is the index. Index equal to this chain length. So this is the index. And now let's try to log previous const previous block equal to this chain index, let's call it chain index, otherwise it can be confusing. Let's see if I do this and I console.log the previous block. 0. This chain length -1. Okay. Chain index is not defined. What? No. Let. It was not defined. No. What? What did I type? Okay. Okay. Block data previous hash. Okay. And now if I type this, five. Interesting. 5. So you are getting very close. Yes. So console log the previous block. This chain index to hash. No. Thank you so much, Tamal. Thank you so much, Tamal. Really appreciate it. So the previous block, so the previous hash property. So this block dot previous hash should be. Let's try this one. It should be the hash. So this, the hash of the previous block. Oh, let's go. Eccolo. Next stage. Oh, this is a good exercise. Okay, validating the chain. Chain validation. Blockchain are run by a network of computers. When a computer finds a new block, it broadcasts its new version of the blockchain to all of its peers. But how is it on social media? Let me check, because I mean every hour I try to post something. Just 50 minutes. Nobody replied. We have this and then this. Okay, we have. Okay. Let's go. Okay. Nice. We are close to 50 likes. Close to 50 likes. Ciao. Ah, I was saying to Francesco Russo, not to me. Don't call me Francesco. Okay, your goal: create an isValid function. Create a function called isValid on our blockchain that will return true or false if a block is valid or invalid, respectively. Okay. We'll convert it into a string. Oh yeah. isValid. So if I do this, I should take maybe I check the first screen. Oh my god. It's saving the logs. We run the tests. Okay. Ah, wow. Okay. Just creating the name of the function. Maybe freecode camp. Each block's previous hash field, and making sure that it's equal to true. Should check the integrity of every block in its chain. To compare the output. So if you do arrays for each, so let's take this dot chain dot for each. Second. You can try to use ChatGPT maybe. Console log like this. Too many parentheses. 1, 2, 3. No. L. Ok. And in this case, it should be here. Okay, so you should check the integrity. So cost ret equal to true if something strange happens internal, and then it should return the red. So we set this value to true, and we check the validity of all the elements in this chain. We do something here, check. And if something strange happens, we will set red to false, and then I think we can just break. And can break the for each, yes. If so, we should check here. Okay. To compare the output of the SHA function, we need to convert into a string. With the previous one. The block hash with the so this is the comparison. So this is block to string, no, block dot hash data. SHA to hash, block to hash, block dot to hash dot to string. Block to hash to string is equal to block dot previous hash dot string. I think we are very close. Hey Yash, it's going well. We are building a blockchain. Let's see. Okay, illegal break, just right, because this is average. Okay, block is not defined. This is valid of every block. Decent. There are some good parts and some parts that I don't like it. Block to hash. Block is not defined. Right. What am I doing here? Okay. I think I need a parenthesis. There is no control. I think I need to add a parenthesis somewhere. For each. Okay. Okay. So it's not block, it's L. No. This is we are defining a method in the blockchain. Can read property of undefined. Nice, Saxon, thank you. Current property string of undefined. So we should console log L dot to hash. Dot to string. To string. Did I put the... Okay. Okay. What am I doing here? That the first one is false. Okay. The problem is that the previous hash should start from 0. Okay, they are not. They didn't say that the first previous hash is 0. Okay, so the first one is correct. No, it's not. No. Wait. This is not previous hash. This is not previous hash. This is this chain. Is this one? This is the previous block. Okay. I think that I got it. So this is can't be this one. This should be a dynamic value. So this is this chain. We need to take this one. We need to take the previous block. This chain. I. This chain I minus 1. Let's see. No. No. Right is true. No, this is correct. This chain minus I minus 1. To hash. Console log. No, we need to log it. We need to take the previous block. Console.log. Let's go. Undefined. Okay, okay, for each element. Okay. Or why is it data undefined? Because I should start... no, let's do a for loop. Because I need to start from the second one. Let's do a for loop. Start with I equal to 0. I equal to 0. I plus plus. I minus then this dot chain dot length console dot log this chain I. Let's try. Okay, logging stuff. Nice, nice, nice. Peter, James. The first one is even past. Okay. Okay. Queen. So this and okay. And now let's okay. If should start from 1 because I can't compare 0 to -1. If I think it's similar to this. Okay, so we are checking this. So this chain I. So if the current element hash to string is equal to the previous element. No, it's different. If it's different, no. Assigned to a constant variable. Should be let. No. Not no. Wait. So we need to compare this one. So let's okay. We need to log this. Okay, so logging the 3 hashes. Now let's log the previous hash property. We have the previous hash property. Nice. Okay. So let's const current equal to and previous. I'm checking the hash. Okay, so current and previous. So if current is different to previous. Return false. Let's see. No, okay, what happened? Con. Okay. Okay. Test 2 and 3 passed. What the hell? What's the problem here? This was the easiest one. So a for loop, it was better to work with. Okay, so what happened here? Current previous. Current previous. No. No. No, 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 no. No, no, no. We have the previous hash in the... Let's make this. I think we are very close. We also got it green before. Current previous, current previous, current previous. What happened here? No, it's the opposite. It's the opposite. So default is should be false. No. Wait, wait, wait. Wait. No. Ah. Ah, this is not a hash method. But this is already a hash. The previous hash is already a hash. I don't need to hash. The previous is just already has the two hash method. You see, they're similar. I think it's just a matter with the index. So the current is I don't think his previous has two hash. No. But this should be. To string current equal to previous. So we have this element, this chain I. So let's like one, one, one. Okay. This should be the same, current and previous. So this chain I to hash to string, this chain I previous hash to string. Let me also, okay, let me log it. This chain, let's see the chain, what does it have? So we have 3 blocks. Okay. Console log. Why does it have the different one? I can't understand. It should be the same. Why they're not the same? See, in the previous he already do the to hash. The previous hash is already previous block to hash. You don't have to do to hash again. Previous hash is the previous block to hash to string. Thus the comparison should be between the previous in the actual block. Thus the comparison should be between the previous in the actual block I think you are right, Marvin. So it should be -1, -1. No. No, wait. No, wait. This chain. Okay, so this is correct. So should check block previous hash, making sure it's equal to the hash of the block before it. Hash of the block before it. So before const before block is equal to -1 to hash Okay. Console.log previous console and the before block. Let's see. Sì. Oh, done. Shout out to Marvin. Amazing. Hi, Aria. How's it going? We make it. We made it. Validated. So let's make a post. As a default, to I'll never get rid of this fame of hating Python. There we go. I have the Docker battle. Okay. There is a giveaway. Just share the live stream link, tag me, and at the end of the live stream, I'll select at least one Udemy course. It can be even more, but at least one. Chat GPT. Okay, should make a break. 51% attack. I'm gonna skip this part because I mean, basically if more than 50% of the network is controlled by someone, all the blockchain concept basically breaks up. Genesis block of Bitcoin. Oh, this is the link. Bitcoin block 0. Minted on 3rd of January 2009. Cool. Yeah, probably I should take a break. Oh, I'm getting to I'm close to 800 subscribers per month. I want to reach 1000. Yes, let's take a break. Break. Be right back. Okay. Let's take some rest. I'll take ginger. Ginseng. Wait. Okay. This is ginseng, is not coffee. So I don't take so too many coffees. Okay. Anyway. Ray, I can also pin messages on Twitch like this. Okay. Nice. Okay. Nice. Let's take it easy, but let's keep going because I really want to dive deep here. So, not very tired, to be honest. I mean, a bit, but okay. I should find a way to make a layout on the desktop as I want. Okay. Okay. Okay, let's try this part very slowly. Confirmation in the numbers of the Genesis block, blockchain, Genesis block, copy link. I'll put this. Let's say someone tagged me so they can participate to the giveaway. We're doing a giveaway. Maybe I should put this message somewhere. Probably I should. Probably I can do something like that. Let's see. should create. Let's go. Let me check. Okay, nice. Dev is participating. Okay, let's go. Okay, let's go. So the nonce of the Genesis block is 2 billions and something. If you take a look at more recent block, the nonce is lower. So the block nonce is actually a 32-bit field. That is the max size of a nonce. What happens when the miner reaches the point? They can change anything else in the block header. Software version, previous block, Merkle, root, timestamp, target. Yes, so basically it doesn't, the first nonce, the nonce doesn't have to start from 0 because it's it depends on many things, so that's it. ECDS node, let's see how is it going. 83%. And this is the week assignment. Video instruction. Local development instead of using our in-house IDE. VS Code. Index.js, Ethereum cryptography. Okay. I don't know if I can do this on a live stream, but I'm gonna try. Okay. So, ECDSA node. The best way to deeply understand blockchain is to put yourself into development mode. Not yet. What would it be like to build your own blockchain? Let's start by applying our knowledge of hashes and digital signatures to our very first project, ECDS node. In this project you will have a simple React front-end which will communicate with a single server. The server will be responsible for transferring balances between accounts. Since it's a single server, it is centralized, so we'll need to trust that the server operator is not malicious. Okay. Your goal, ECDSA. This project begins with a client that is allowed to transfer any fund from an account to another account. That's not very secure. By applying digital signatures, we can require that only the user with appropriate private key can create a signature that will allow them to move funds from one account to the other. Then the server can verify the signature to move funds from one account to another. 1. Incorporate public key cryptography so transfers can only be completed with a valid signature. 2. The person sending the transaction should have to verify that they own the private key corresponding to the address that is sending funds. Okay, while you're working through this project, consider the security implications of your implementation decisions. What if someone intercepts a valid signature? Would they be able to replay the transfer by sending it back to the server? Setup instruction. Video instruction. I'm not gonna watch the video, but let's see how long it is.
I'm gonna go over the Exta node project and show you how to...
30 minutes. Okay, I'm gonna skip this now. Written instructions. For this project you're going to be doing local development instead of using our in-house IDE. This means that you need a few extra things to set up. Download a code editor if you don't already have one. We recommend using VS Code, however feel free to choose whichever editor you prefer. Clone the repository locally, GitHub, by running the following command from your command line. I don't know if this works, but let's see. Okay, they don't have a... Okay. There we go. So we have a client, a server. Cool. Very cool. I like this thing. Beat. Up. Ah, it's really React. Okay. Let's try. Let's take a look at least. But I don't know if I'll do, because I like the think of the tutorial, but I don't know, for something like that, I don't know. Let's see. I really can't find it. No, misclicked. For the readme instructions to learn how to run the project, make sure to run the client and server as two separate processes. Once you get up and running, you notice a few components that we are given to start. Wallet addresses, index, the left-hand side of the UI, the right-hand side, okay, tips. But, so this is an assignment. I don't know if I want to keep going with the tutorial or doing the assignment now. But I think I'll do the tutorial because it's more engaging. Like here I can really struggle for hours. So. I mean, let's take a look. What is the instruction? Client folder? Server folder? Where are the instruction? I don't understand. Where are the there are not the instructions. Few components that we are given to start. Ah, it's no. This is just transferring balances between accounts. Okay. Let's test it. So we can do on wait, let's follow the readme. Open the client folder. Let's go on the client folder, npm install. npm run dev. Okay. This is the UI. Then we can do this. And here we can go on server. npm install. Node. No, what did I do? Nah. Install the dependencies in the server, and now node index. Only just 40 lines of code. Okay. Okay, but there are no instructions here. Probably I should watch all of these. There are not written instructions. I'm not gonna watch 30 minutes video now, for sure. And
where we learned how to recover keys.
Recover keys.
Let's say const.
Okay, so here he's explaining, but this is not a tutorial. This assignment. I'm gonna skip the assignment because I don't know if it fits for a live stream. It can be too long. No, don't like it. Congrats on finishing week 1. We need the assignment, of course. Learning retrospective. Foundations of blockchain technology, cryptography. We broke down the building blocks of blockchain and even created our own simple chain containing blocks of data. Summarize, hash functions. I like the recap at the end of the section. Public key, consensus mechanism. Next step, share a recap on Twitter. Next week. Okay. Okay, so let's go on the second part. Okay. Okay. Also, I don't know, there is not like a check for this assignment. I mean, it's okay, but it's UTXO and account models. Not gonna watch this. Let's see how long it is.
Let's
Is he in underground? Okay. Okay. Okay, so with traditional Web 2 server-based platforms, keeping track of user data and information is actually a lot easier than it is on the blockchain. This is because there is a single centralized server that stores the state of user's account. There's no need for consensus or resolving discrepancies, okay, since there is only one central place that stores information. However, when you move to the centralized system, the problem of storing user balances becomes tricky. The centralized networks like Bitcoin and Ethereum need specific models for keeping track of the state of users. Bitcoin uses the UTXO model to keep track of users' balances. Unspent transactions output. Ethereum and other EVM, Ethereum virtual machine chains, use the account model to keep track of user balances. Let's dig in further. UTXO stands for Unspent Transaction Output. You will see the term UTXO used a bit in this lesson. Bitcoin uses the UTXO model, so we like to include it because it helps us understand trade-offs in blockchain storage model, as well as it will help us compare and contrast with Ethereum and its use of the account model. Okay. You thought we would already be learning Solidity, huh? Ah well, we're starting from scratch and digging into the fundamentals of what makes blockchain tick. It is important to understand this concept as they will make you a better rounded smart contract engineer. Let's dig in. Okay, transactions. The best place to start before looking at how blockchain keep track of user balances is the place where users' balances begin, the transaction. Let's explore with the following questions. What do we need in a transaction? So, 3. Amount of the amount to send. We need the payer and payee. Okay, the sender and receiver, basically. Since we're working in a system based on really secure cryptography, we need one more thing to complete everything required for a successful blockchain transaction. pair authorization, some sort of unfakeable authorization given by the initiator of the transaction. Okay. Now, the fourth item will just end up being the digital signature, which is basically a hash that is extremely hard to replicate if you do not have the correct inputs. In this case, a user's private keys. Without the private keys, a payment authorization cannot occur. The only way to do it would be to hack basically cryptography, which is practically impossible. Digital signatures are very important. Make sure to review week 1, day 2 if you still feel shaky on the subject. Okay, what is the purpose of a transaction? To change some user state, right? If Alice sends Bob $5 die, I don't know what is that. Alice $dollar die, balance should go -5, Bob's should go +5. Alice's transaction is responsible for changing the state of their balances. Changing state is extremely important in blockchains, which are typically transaction-based networks, so keep this in mind. Bitcoin, Ethereum, and regular banks rely on transaction-based models to keep track of users' balances. Let's take a further look below. Okay, so account-based model. If you have a bank account, you are very familiar with this model of keeping track of user balances. The account model follows just that, accounts. It tracks the balances of users based on their overall account state, without any tracking on what constitutes the actual balance itself. In other words, an account-based ledger would mark an entry like this. Okay. Like this. Okay. Notice how the state of the account is kept very high level. Rick's account balance is $1 and cent amount, and that's it. There is no further information tracked on what the breakdown of the balance is. For example, $142.62 is one $100 bill, one $20 bill, two $10 bills, 8 quarters, 5 dimes, 2 nickels, 2 pennies. Okay. When Rick goes to the ATM and withdraws from his balance, he gets in whatever bills plus change the bank has at hand, not in the exact change it took to make up the balance in the first place. Right. I got $200 from the ATM, and I got all in 10 in 10 euros bill. What does a transaction look like in an account-based model? Alice has $60 total balance, Bob has $20 total balance, Bob sent Alice $5, Bob's balance is subtracted 5, if the remaining balance is greater than 0, proceed then revert. Alice's balance is summed 5. The ledger is marked in both ends to update total balances, and that is the end of the transaction in an account-based model. This might seem weird. Why would we want to keep track of these details for something as simple as a total balance? We'll look... Yeah, Marco, how's it going? We will look a model for keeping users' balances that does include this feature, the UTXO model. Okay. Ethereum uses the account-based model, while Bitcoin uses the UTXO. So this is more for Bitcoin. Okay. Short for unspent transactions outputs, to keep track of user state balances. The UTXO model differs pretty drastically from the account model. It is a little bit more complex. Doing stuff, thank you, I'm doing well. The UTXO model differs pretty drastically from the account model. It is a little bit more complex, mainly because it is not a familiar interface like the account model is. So why are you doing this? Yet it does set up some interesting features. Alice sends Bob 5 bitcoins in the 4... Wow, 5 bitcoins. of a transaction related to the Bitcoin network. At this point in the transaction, if the transaction is valid, Alice is signaling an intent to change the user state. When the Bitcoin network mines Alice's transaction, Bob is credited with a UTXO worth 5 Bitcoin. This is how the Bitcoin network keeps track of user balances. It keeps a really big long set of UTXOs output out of state changing transaction. So when people say I own 3 Bitcoins, they should really be saying I own some UTXOs that allows me to spend 3 Bitcoins. Okay. All UTXOs are non-fungible. Okay. To spend a UTXO, you must refer back to that specific UTXO. Okay. Okay. Once a UTXO is consumed, any leftover change from the transaction creates new UTXOs representing the change amount. The UTXO, often referred to as a coin, can only be spent once, no double spending, of course. In Bitcoin, each UTXO has a script associated. Okay. So let's see here, accounts versus UTXO model. So accounts, user accounts, there we go, Jax. User balances, overall account state, and for UTXO like Bitcoin, you have a specific one. Okay, so Ethereum has just an overall account state. It seems simpler. Account, so pros more intuitive, UTXO very good privacy. Okay. Cons, replay attacks, cons that are stateless, a complicated state-heavy design. Okay. Conclusion, deciding what model to go with is a game of design trade-offs. Ethereum's use the account-based model transactions must be more flexible to account for the many moving pieces of state in the system. Bitcoin uses UTXOs as it is a network purposely designed to be as simple and stateless as possible. Okay, one more and then we will start coding. Just a reminder that we have, no, where is the, no, we're losing it. Okay, so UTXO example 1. Bob runs a Bitcoin miner. He successfully computes a block and rewards himself with a 12.5 Bitcoin as per the emission rules. This is a brand new unspent transaction output Bob has introduced to the system. Now let's say Bob wants to send Alice 6.0 Bitcoin. He can do so by using his UTXO with 12.5 Bitcoin. But wait, Bob doesn't want to send Alice 12.5 Bitcoin. How do we handle the remainder? Maybe here is a typo, I don't know. As it turns out, Bitcoin allows you to designate multiple outputs per transaction. In this particular transaction, we'll create one UTXO as 6.0 Bitcoin for Alice and another UTXO of 6.5 Bitcoin for Bob, the reminder. Then we'll mark the UTXO for 12.5 Bitcoin as spent, since it was used as an input for the transaction. Okay, UTXO example 2. One thing that can often happen when using this model is users end up with a lot of small UTXOs. As Alice transacts with the network her UTXO breaks up into smaller outputs until she's left with 3 UTXOs of values, 1, 1.5 and 0.8. Okay. Let's say that Alice wants to purchase something for 3.0 Bitcoin. She can do so by specifying many inputs into the transaction. She can put all 3 of her UTXOs as inputs into the transaction to a total of 3.3 Bitcoin. After the transaction is executed, she will receive a new UTXO of 0.3 Bitcoin and her previously inputs will be all marked as spent. Okay, that's enough. Let's go. Let's go to something because... okay, so this is more JavaScript stuff. Okay, I can read like that. Okay, let's see if we... okay, let's go. Just want to check Twitter 1 second. Just want to check for hours. No, we have some time now yet. Okay. Okay. Next time, now it's time to create an object for transaction outputs. Okay, using a Bitcoin block explorer, you can look up TXOs on the actual network. If we wanted to look up UTXOs for a particular address, okay, the value after active is an address. This particular address was the one Satoshi used when they minted the first Bitcoin block. Okay, your goal: create a TXO class. Let's complete the constructor and spend. So basically this is JavaScript, okay, but we are applying the concept on this UTXO. So constructor and spend methods for the TXO class in the txo.js file, so this file. The constructor should store the values passed into it and property of the same name. Should also create a property spent and default to false. Okay. So this it's not very beginner friendly, but okay. This dot amount equal to amount, and then another property which is this dot spent equal to false. Okay, so this is what they asked and this is what it means. The spend function should set the spent property to true. Okay. Okay. Notice how spent is initially false and you create the new TXO. After invoking the spend function, spend should be set to true. Let's see if I can make it the first time. Done. Without errors. Let's go. Okay. Transactions on the Bitcoin network can have many input and many outputs. You can take a look at this Bitcoin transaction. No. The combined with a scripting system, its transactions allows Bitcoin users to engage in more complex financial agreements than a one individual simply sending money to the other. Okay. Your goal: ensure inputs are UTXOs. On this stage, we introduce a new file, transaction.js. In the transaction constructor, you will see two arguments passed in. This is how the argument: input to TXOs, output to out. Okay, this is hard to spell. Both of these objects are arrays containing. Okay, so these are arrays containing instances of transactions inputs. Store input TXOs and output TXOs on the transaction object. On the transaction object. Okay. Basically this. So. Okay. In the execute function, do one thing for now. Ensure that none of the input TXOs are already spent. You can't allow double spending TXOs. Throw an error in execute if any input TXO is already spent. Throw an error. Throw. Okay. So. Check. Check input TXOs. So if I do console.log, so let's log it. 5 hours already, cool. This. Okay. Basically this is okay, so let's do this for each. Okay, so the for each, and then let's log it. I'm testing if there is any of the element in the TX in the input UTX O's arrays and as any spent, which is true. If that's true, if it's true, we need to throw an error because it means that it's already been spent. Okay, makes sense. Console.log element. That's this. Let's run it. No, what am I doing here? It's very hard to write stuff without the editor. Okay, nice. Very easy now. It's very easy. It's very easy. So basically, if element dot spent is equal to true, first of all we log that there is an error, and then we throw it. Let's see. I should see the error only on the second one. Try. True. You see here the error. Throw new error. Throw new error. Like this. Done. No double spending in this house. Let's go. Okay. This is long. Inputs and outputs. With a multitude of input and output UTXOs allowed in every transaction, there are many possibilities of exchange that exist. Bitcoin wallet software will sometimes choose to include many input UTXOs, just to aggregate them into one bigger UTXOs to send back to the owner. For instance, if you have 5 UTXOs, each with amounts of 0.1 Bitcoin, your wallet may choose to combine them into 0.5 Bitcoin on the next transaction. Behind the scenes magic. The important part is ensuring that there is enough total value in the input UTXOs to cover the total amount in the output UTXOs. Okay, your goal. Let's make sure that the input UTXOs have enough total value in them to cover the total value of the output. Okay, so basically, like we spent many things, so we made like a total, I think. If the total value of the input is less than the total value of the output, throw an error in the execute function. I left some comments and... Okay. Okay, so first of all, let's log this array because I don't know how it's done. Console.log this. What's... Okay. Let me remove the other console logs. Owner amount. Okay, so if the total value of the input is okay, let's make sure that the input TXOs have enough total value in them to cover the total. Okay, so basically we need to sum the value of an array. Easy. Okay, so let's remove this. Let's make it a bit bigger. Okay, so basically we can do something like this. So let's do another for each. Make sure that the input enough total value. Sum the input UTXOs. If okay, so first of all, so in this for each we should just console.log the L.amount and then we sum it. Okay, this part should be relatively easy. Okay, 5 and 5. So we should let total inputs equal. So we basically start with this one and then total inputs plus equal L amount. Okay, at the end of this we make another console log, the console.log total inputs. Are enjoying this? How is it going? Not many people today, but it's okay. Run tests. Total inputs 10. Okay. Now we do the total output. Total okay, there is a typo. Total inputs should be capital. Okay, total input, total outputs. So let's take the outputs and we do exactly the same. So this amount, and we sum all the and then we throw an error. Total outputs. Okay, I avoided the stupid error. Okay, 10, 10. Okay. And then here at the end, we throw an error. If, very easy, if total inputs, basically we don't want to allow you to spend more than what you have. If total inputs in less than total outputs, I'll do like this. Very easy for now. Let's go. 3, 2, 1, done. Bam. Okay. Successful transaction. When a transaction is successful and mined to the blockchain, the output UTXOs become new TXOs that are ready to be spent. the input need to be marked as spent to ensure that they are not spent again. After all, the whole purpose of the blockchain is to fix the double spend problem. Your goal: mark inputs as spent. If no error are thrown during execute, then it's successful. If no error are thrown during the your goal: mark inputs as spent. So mark inputs as spent. So I think that in this case it's very easy. So we have another for each. So let's go with the for each. So basically we want to set, let me show you. So console.log. So let's try to do this in the proper way, because I think I know what I'm doing. So let me do this, let me remove this. So let's log the input thing. So basically we have like something that we want to spend, but it's not a single transaction. Maybe we don't know, like we want to buy like 5 things. Okay, so let's log it. Don't mind errors, just check the logs. 5573. So it seems it's like if I want to buy €5, €5, €7, €3. Okay, now the thing is this. Second, I have too many logs. Log. I was already doing the log of this. Okay, so here. Second, this is okay. So in this case we throw an error. In this case we want to, can you see here is spent false, false. So we want to set the values to spent to true, and this is very easy because we can just not output but input. So here we will, after this, so set all spent properties to true. Spent to true, it means that we spent them. Okay, l.spent equal to true. Okay, we just spent everything to true. Let's go. Done. Okay. If you want me to explain something, just let me know. Let's go in the next one. Miner's fee. At this point you might be wondering why in the third stage, the way I never did this tutorial before, just checking this for the first time with you. The total input amount be more than. Okay, shouldn't we also throw an error when the output amount turn out to be less? Yes. No. Okay. The remainder is given to the miner. Okay. Right. Okay. They tricked me. Calculate the fee. Calculate the fee. At the end of the execute function, calculate the fee as the sum of all the inputs minus. Given that we throw an error, if the input are insufficient, the number should be at least 0. Okay, given that we throw okay, and let's removing stuff, so this is a bit better. Okay, nice. So Given given that we throw an error if the input are insufficient, this number should be at least 0. The inputs are insufficient. Okay. This number should be so. Anytime outputs are less, this should be a positive fee. Okay. Store the fee amount in a property called fee. Okay, if the inputs are insufficient. If what is the total input? Allora, let's log it. Console.log total inputs. I think it's asking about this. Total inputs. Let's see. Let's see if I'm getting what they are asking for. Not sure 100%. No. They're never reaching this. Should have a 0 fee. Okay, but wait. Okay. In the constructor, this fee equals 0. Okay, calm down. Okay, I added this property. But why is not logging it? Should have the reminder as the fee. Should have the reminder as the fee. The reminder. Should have the reminder. Okay. Why I don't see the console.log? Okay. Let me put this something here. Should have the reminder as the fee. Okay, but thank you, Marco. Thank you, Marco. I can also pin stuff here. Hey, I can pin. No, what the Oh, Twitch chat highlight. There we go. I also a Twitch chat highlight now. Twitch chat highlight and YouTube chat highlight. Perfect. Okay. So, store the fee amount in a property called fee on a store the fee amount. Totally understandable. Transaction execute. Should. But this is the sum. But this should be done at the end. This dot fee equal to total output minus total inputs. Okay. No, it's the opposite. Okay, nice. Nothing for free, not even a transaction fee. Yo. Further reading on UTXOs, some information. Genesis block. The script pub key is also called a witness script. For each locking script, there should be an unblocking script. Okay. To unlock the UTXO and allow it to spend. Typically, all the unlocking script needs to provide is a signature that verifies ownership of a public key, and then the public key needs to match the address after being hashed twice. Okay. Bitcoin script. The Bitcoin script language is meant to be a simple stacked-based language that has no loops, so it will always resolve and there are no denial of service attacks. The language is basically a list of function-like operation codes that take arguments of the stack and operate on them. Well, yes, we can say yes, because on social media, I make collaborations, I make presentations, so yes. I'm currently a developer advocate, not for a Web3 company, but I work in DevRel and I do stuff. So, business and Stack Overflow. Two common forms of transaction scripts for Bitcoin are the pay to pub key hash and pay to script hash. Okay. And now 3 data structures. Okay, let's go. Back to computer science. I never get rid of data structures. Blockchain network use transactions to change state and keep track of user balances, as we saw in the previous section. Let's dig even further into the complexity of these systems and start looking at what data structures they use to store all the changing state data. We will, I think maybe at some point we will reach also the Merkle trees, but let's start with a tree. Okay, the tree, okay, this is a joke. Let's go faster, please. Just feel like in real life there are many kind of trees. Okay. Node in the tree. Network nodes, simple tree. Okay. The top orange. Okay, let's talk about the terminology a bit. So this is like the root, the part. Now this is the parent. And this is okay. So they should put like 3 dots here. So it's like, I don't know. Technically, it's the parent. The fact that it's not aligned is giving me HDAD. ADHD. The top orange is self-transparent, while the bottom green nodes should be read as the children. Okay. Binary tree. Binary tree is a tree where all the every parent has exactly 2 children. It sounds crazy in natural language, but that's it. They're not centered. I hate it. It is typical to see some enforcement property before tree to distinguish between types of tree data structures. A tree is considered binary when each parent has at most, not exactly 2, but at most 2 children. The key word is in this tree is binary. It, like other preceding terms to tree, sets some type of rule for the tree, in this case that each parent node can have at most 2 children. Okay. Notice that tree in the diagram above now has 4 new gray nodes. This would now be referred as leaves, since they are the last level. So the last level of trees are leaves. So tree. Okay. The tree above shows that a tree can be any parent with any number of children. There doesn't have to be any enforcement on the tree. It's just a tree of data. Okay. Enforcement allows people to more efficiently work with data since they know a tree will have a certain rule enforced. But the point is, a tree can just be a tree. Tree versus linked list. Okay, this part is interesting, okay? A linked list is also a tree. Just a really long one that only has one child per parent in a long continuous chain. Okay, now interesting. A tree is not necessarily a linked list. Here the two code implementations for a linked list node and a tree node to help distinguish. So, linked list node, constructor, this data, this next null. We made this in the first section when we worked on JavaScript. Instead, a tree node, it has this data, but it has this. So the children of a tree node is an array, and that's the huge difference. So a tree node can have just one children, but it's not limited to have just one children. Is it better? Worse? It's different. It's a different data structure. Notice that tree node holds the typical data and an array that contains a reference to any children in the parent node. The linked list node just keeps track of one next node, and it can be null if it's the last of the linked list. Tree vocabulary summary. Okay, I like this one. Okay. Oh, this is nice. Root, edge, the key of the parent, children, okay, these siblings. So it's basically two nodes that have the same parent, a parent in common, height of the tree, and leaf nodes are the last. In this case, the leaf nodes are these, but also these. Okay, and this is a subtree. Subtree can still be a tree. Nice. Okay. Now, when to use a tree? Sometimes trees occur quite naturally. File system. Tree usage. If your data can be stored hierarchically, using a tree can be a good data structure to go with. A tree is also a very efficient data structure for the searching and sorting of data. Recursing algorithms are often used in conjunction with trees. Trees can be very efficient data structures for searching, sorting data precisely because of the rules it sets, like being a binary tree or an even structure rule set, a binary search tree. Okay, binary search tree. Interesting. So, I worked with this BST, I worked with them a lot. Hell. But it was many years ago. A binary search tree has the following properties. Let's put with this. It's a binary tree. A binary search tree is a binary tree. The left subtree of a node contains only node with keys lesser than the node key, and the right subtree contains only node with keys greater than the node key, for example. And this is true also for the subtrees. Each node, the left and right subtrees, will also be a binary search tree. So let me repeat. So as you can see here, if we take, for example, the root, we have the 4, which is less, and 12 is more. Not just that, but also all the numbers here on the left, they are smaller than 9. All the numbers here here are bigger than 9. That's not enough. Every right and left subtree, for example this one, they have to be a binary search tree, so they should keep the structure. Okay. Spoiler. Binary search tree trivia. Knowing that each left child is less than the parent and each right child is greater than the parent, how many attempts does it take you to find a number key? Logarithmic time. Adding a whole new layer of elements adds only one more search attempts at words. Because of the BST, short for BS binary search tree, enforcement properties, the search time always remains O log n, where n is the number of nodes in the tree. The tree in the diagram above is a BST of a height, or how many levels a tree has, or tree with nodes held at each level that increases in number by a power of 2 each level down. The last level contains 4 nodes, which means the next level under that will contain 8 nodes at most. Where is the real magic of enforced property trees like BSTs? Even though we add a whole new level of new data, the search time all increases by 1. In the word, as the size of the tree grows at an exponential, the search time always remains O log n. Here is a chart to visualize, and here is just to understand the complexity of an algorithm. But like the logarithm, it's it's way less than what you see here. For example, I don't know, if you have 1,000th element, it will take at most 9 or 10. Okay, so interesting. Since blockchains are basically databases, big O analysis is very important to help choose the most efficient data structure, low storage cost, easy search and retrieval. When designing a system with data needs, you want your data structure to be as close to constant time as possible. Big O notation gives us a rough indicator of how well an algorithm will perform in terms of n. We want our algorithm to be efficient. Conclusion: we covered basic tree data structures, different types of enforcement on trees, and general tree data structure vocabulary. Merkle trees are for blockchain, 2 sections, tree time. Build a binary search tree. Oh my god, again. In programming, trees are a data structure that come up surprisingly often. They have a number of different use cases ranging from efficient data storage to representing a file hierarchy. In this we crossed 5 hours already. Cool. Okay. Tree starts with a root node which branches the nodes underneath its children. The word binary indicates that each node has at most 2 children. It's called a search tree because the order of the node is sorted by the value of the data. Okay. Any child to the left is part smaller. We already talked about this. Let's go to the code. Okay. Creating a node. Let's first create the class node, from which we will create each element inside of our tree. The node should contain data, which in this case is 5. It should also contain a reference to the left child and the right child. Your goal: complete the constructor. Okay. Complete the constructor function on the node. Store the data inside a data property on the instance. This, in layman terms, is this. So that the data property, we do this typing this.data, and data is this parameter that passes here. Store null in properties left and right. Properties, so we have this.left equal to null and this.right equal to null. So this is exactly this. A node with some data, can be 5, can be anything you want. Sometimes it's convenient working with numbers, but left and right are null for now. Let's see if I make it to the first try. Done. We'll work on tree.js. Okay. It's time to create our tree. A tree will keep track of one property, a reference to the root node. So your goal is store the root. Okay. So this is the node class node. This is the class tree, which is made up by nodes, but not just the nodes. Finish the constructor. Okay. What we need to do is to store null on a root property. So this dot root equal to null. This is exactly what is saying here. Store null, so this dot root, which is a property of the tree, is null. Let's see. Done. Let's start adding nodes. So this is a tree, this is an empty tree, like the 0 for the numbers, okay? Now, adding a root. In this stage, we'll create a new method for adding nodes to our tree. This is a difficult task to generalize, so we'll attack it piece by piece. Okay, let's start by adding a root to an empty tree. Your goal: add node method. So we need a method to add the node. Create a new method add node on tree. So tree, on the class tree, we add a method which will take a new node. So this is the name of the method, add node on tree, which will take a new node. So this will take a node, take it, and add it to the tree. Assume that the tree is empty for this stage. Simply set the root to be the node passed into the method. So this dot root, which is a property of the tree, is equal to the node. Okay? Call me mad, but I like this part. Done. Yay. Let's build on our add node function in its next stage. Let's go. First layer. Now it's time to focus on adding the first layer of nodes underneath our root. The bottommost layer of a tree is called its leaves. Keep it the code you use to pass the last stage, and then add another case for when a root already exists. When the root already exists, we'll need to decide which side to add the new leaf node to. So I think we are you're implementing not a normal tree, but we are implementing a binary search tree. Okay, so when the root already exists, we need to decide if the new node data is less than the root data, we will want to add it to the left. Conversely, on the contrary, if the data is greater, we want to do the right. So modify add node. Modify the add node function to also handle adding the first children to the root. Adding the first children. The first children. Okay. Also, so this is something else. Modify add node. Handle adding the first children. So this is the root. You can help me, by the way. If node data. So console.log. So because here we get the node. So if we log the node data, we should see numbers here. Okay, so I see numbers 3, 7. Okay. Okay, so if so we have this root. I applied to the bootcamp. Do you know if it takes a long time? I don't know, Marco, but I know that you should get access soon, I hope. So if okay, so let's try to to do this. If the new, thank you, let me see how it looks. Cool, like this. So if this dot root is greater than this root data no wait let's see this. If this dot root is equal to null, so if there is no root, we do this. Okay, else. So this is root already exists. So we need to check. So if this dot root dot data is greater than node data dot data, so if this root data is greater than node data, this dot root dot left is equal to node, else this dot node dot right is equal to node. So let's see if it works. If it works, I'll explain. Okay. No. Property right of undefined. Okay. Oh, of undefined. Okay. This root, right? Okay, working. So let me explain again what I'm doing here. So we are creating this structure. We have this root node, we have the left and the right. So we want, so if there is no root, the node passed to add the node, so like the first one, it will become the root. If the root already exists, we have two choices. So if we get a smaller number, we'll put this on the left. If we have a greater number, we'll have this on the right. But can we log it? No. Is there a way to log this tree? Maybe not yet. Okay. I'm enjoying this part. Let's go on the next one. Many layers. Okay, so now it's time to make our add node function work for many layers of the tree. Okay. For help on designing your solution, okay, you can do it iteratively or recursively. Your goal generalize. Complete the function add node so that if it can handle adding nodes no matter how large the tree gets. Don't worry if you start to get frustrated. This is a tough stage. Okay, this is not easy, I think. Let's see. I want to think a bit and then I'll start using maybe ChatGPT or Stack Overflow. So okay, so let's say that now we bet a bigger one. Basically, we're asking us to implement a binary search tree, okay? To write a recursive solution, let's do it. You already wrote the code to add a node underneath another node. Apply this recursively. Write a new function or a tree that will take two arguments, a parent and a child. This function should add the child under the parent node. If the child data is less than the parent data, then it should go left. If the parent already has a left node, call this new function recursively with that left node as a parent. If the parent does not have a left node, set the new node as the new left node, okay? if the child data is greater, if the parent does not have a left node, set the new node as the new left node. Okay. If the child data is greater than the parent data, then it should go right. If the parent already has a right node, call this new function recursively with that right node as the parent. Now you can call this method from add node if there is an existing root. Okay. So you can help here, because this is not an easy task for sure. Also, this is add recursive as to parent and child. Should add the child under the parent node. Just add under the parent node. Okay. If child dot data is less than the parent dot data, it could go so parent already should go left. Else go right. Okay, makes sense. Go right. So go left and go right. Okay. But here, okay, if the parent already has a node, if the parent dot left is equal to null, it's easy. Parent dot left equal to child. Okay. And here is the same. If parent dot right is equal to null, parent dot right equal to child. Okay. Else we call this new function recursively. So add recursive makes sense to me. Add recursive with that left node as a parent. With that left node as a parent. That left node. That node as a parent. So parent dot left child. It should be like that. Instead here, else okay, makes sense. Okay, now you can call this method. Okay, so this add node. Okay, so else maybe let's do this. Add recursive. The root will be the parent. This dot root and this node. Does it make sense? I don't know. Let's see. No. If parent left. No. If it's just this. Okay. The dumbest stuff ever. The dumbest stuff ever. Okay. This. Let's see. No? Add recursive is not a function. Because this should be declared before. No. Add recursive is not defined. $29. Here. Like this. Oh! Ooh. Very close. Oh, super close. 19. Let's go, let's go. Oh, ho, ho. Amazing. So I did a couple of dumb mistakes, but this is a nice implementation. I have to say that the explanation was on point. So it was very well explained in natural language. So I just had basically to translate what was written here. So I didn't do much, but I just turned this into code. Julia, I'm hungry. I'm wearing the blue light. Is it better? Let's see at the end of the day if my eyes are less tired. Let's go. You see? Do you like this overlay? Julia helped me with the overlay, so I'll give a shout out at the end. Not very hard. There we go. This is a live stream. Now this is a live stream. Nice, nice, nice. We have increased the level. Now just have to understand how to code. Julia is participating in the Udemy course. So Julia is participating in the Udemy course giveaway. Okay. I don't think Julia knows what Udemy is. There we go. Okay, almost 6 hours. Let's go. Search. I knew. I mean, if I can do all could be cool. Search tree. It's time to reap the rewards of creating our binary search tree. That's right, it's time to search. Let's use the sort order to find the nodes in the tree. Okay. We start at the root 5. Recognize that 4 is less than 5, so we move left. Giveaway, a free course. Paid free course to learn something. Doesn't have to be programming. It can be about a language, it can be something. There is a platform where you can basically buy paid courses. And to participate you had to share the link of the live stream and tag me. So you made it. Maybe you didn't know the rules, but you made it. And if Julia wants the giveaway, I'll give another course. Okay, so we started the root 5. Recognize that 4 is less than okay. Your goal. Has node method. Add a method has node that will take a number and search. So here, take a number, inside the data property as number. Okay. So search binary search tree implementing the search functionality. So let's start with this root. The void. No, data dev. I have a surprise. We have the overlay. Finally, Francesco made it. Let's go. So search inside this data property. So if if this dot root dot data is equal to number, return true. Should take maybe one green. Okay, so we can try to implement. Nice. This overlay is nice. So we should search recursively. I mean, if I can do this, number your rating. What do you mean? Your rating of Alchemy? Ah, my rating. Five. So far, many things that could be better. Anyway, so search recursively. I never made the FreeCodeCamp. I didn't learn with FreeCodeCamp. I think at FreeCodeCamp maybe it's more structured, but I never tried it. I should. So So we need a recursive way. Maybe we can try ChatGPT. Let's see. But I mean, the idea is the same. So we search recursively. So we have this, and we search recursive in here. I don't know if we need the root. Search recursive, and then here there is a test. Okay. So the search, we can search recursively on the children. So if number is lower than the root, then this dot root, search left, else search right. So if the number is smaller than the root, so if the number is exactly the root, return true. If else, if number is root, okay. Search left, search right. I don't know if I want to implement it. Probably I'll try some help here. But anyway, numbers minus number. This is means that is search left. So we'll probably need a search recursive. Wait. If I just do this. If the number is less than this root, I can try has number. Number. I think we need a has recursive, very similar to this. A search recursive parent child, I think. Okay. 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 Let's try to use ChatGPT here. I can try to search recursive parent child. If the number is greater, search left, search right, and a search should be a search recursive with a parent and a child. Okay, wait. Search recursive. This search recursive. Hey there, Toby Loba. With a parent and a child, so is this dot root dot left number. Okay, makes sense. Okay, 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 okay. Search recursive, search recursive, search recursive. Okay. If parent number node parent if console.log search recursively. Okay, nice. So let's see if it's working for now, apart at least. 3 has node is not a function. As node. Node, no, it's not. Okay. Oh. Oh, it's almost solved. Searching recursively. Okay. Searching recursively, and then parent and number. We are very close. We are very close. I mean, if I implemented recursively null 3 null. If so, if parent equal null, if this dot root, no, you just have to say this, if parent equal parent return okay. They're very close. Okay, searching recursively null 3. Search recursively node 3. We're very close. We're very close. Just 3 tests are not passing. Searching recursively. Okay. We're very close. Oh my god. Return true. Okay. Hey Madhu, how's it going? We're implementing binary search tree. Search recursively. Is parent is equal to null. Okay. Okay. Looking for number. Nice, Madhu. Looking for 5. Past. Looking for your sessions. What does it mean? Looking for 4. Okay. Looking for 3. Search recursively. But is this okay? Where is that structure? Is this a structure? No. We are so close. So close. Looking for 3. Search recursively, not 3. Should find 3. Did not find a node with data 3. Why? So. Okay. Search recursively, but why is it null? Console.log. I think looking for 3, searching left. Oh, searching right. Okay. Looking for 3, searching right. Okay. Root is what? Looking for 4. So root is number is I see I think I made just a small mistake. For right, root is 5, number is 4. If number, root data. Okay. parent is not null. Okay. Okay. We are... Okay. Parent is not null. So we are going search recursive search else this search. Okay, we are already searching recursive. If parent is equal to null, return false. Otherwise, else. If parent dot data is equal to number, return true. Otherwise, this recursive course no, you're very close. It's so close. Because the logic of going right and left should not be here. Should just be here. The logic of going left and right should be in the recursive. If is this one. If else. Okay. This is a recursive method. Okay. Else console.log searching recursively. Okay, and this is this dot search recursive. Just search recursive with I don't know. Search recursive, yes, with the wait. The logic is here. This search recursive, this root, okay. This search recursive, this dot root and number. Let's see. Add. Okay, so to add the node, this search recursive, this root and node. Because in this case it goes here. Go with the recursive with parent and child. Okay. And here the logic is here. If number, okay. Parent and number. Searching recursively parent and number. So if parent is equal to null, return false. Makes sense. If parent is data is not, if parent data is greater than the number, we just search recursive on the parent dot write if parent dot data is equal to number, return true. If parent data is greater than number, search recursive parent right number. Else, search recursive on the left. I don't know what I made. Ooh. Search recursive this. Wow, if I did this on a live stream, it's amazing. Ooh. Okay. Did not find a node. Right null. Okay. Search recursively. Parent.data number. Let's try like this. Okay. Okay. Searching recursively. 5 and 3. Five, 3. No, if... No, it's the opposite. Searching recursively. Parent data. That should return. Return. Search recursively. Okay. I think we are super close. I want to... Okay, let's do it. So, if... So, search recursively, 5 and 4, 3 and 4, 3 and 3. Did not find a node with data 3. But why? Add node, search recursive. Parent data, console log, parent data. If parent data is equal to the number, return true. Console.log, found it. Let's see. Found it. Return true. What? Okay. Return. Okay. Return this. because we have all the calls. Did not find a node. This is the last step because this is found it. So this should return true and stop everything. Okay, let's use ChatGPT, but I think we are very close. Search tree. So implement binary search tree recursively JavaScript. Let's see if it's better than me, probably. Let's see. I think I was very close. Okay, binary search tree, root null. Let's see. Okay. Let's see. I'll just ask for the recursion. Oh, it's doing the whole implementation, but it was not what I was looking for. Let's see. It's literally like this. Search. I think this is not correct. Let's see here if search not in value, not data. Hey there. Return this search. Not this route. No, this search recursive. This is correct. It's correct. Parent right. If value, if number minus that node data. Okay, parent right. The problem is that I found it. So if it says found it, return true. I don't know why. Well, let's see. So the has node. So let's see what happens with 4 and 5. So looking for 4. Is equal? No. So then return this search with this root. So this is 5 and 4. Search recursively. Okay, search recursively for. Search recursively with 5 and 3. Search recursively with 5 and 3. If parent data is equal to number, found it. Return true. Otherwise, else. So skips. Here it goes here. Huh? Let's put it here. Let's see. No. Did not find a node with data 3. Why? So if parent is equal to null, so if parent is equal to null, basically return false. Otherwise, if parent data is equal to the number, console return true, found it. Otherwise, if parent data, okay, so let's see, 5, 3. So search recursively, 5, 3. No, 5 is minus the 3. If number is greater than parent data, console.log, we are got in there searching right recursively. Otherwise, let's see. So 5, 3, search recursively right, but the number is 3. If the number is search recursively parent left, and here is parent right. Right. I can't find it. Looking for 3. Searching recursively 5 and 3. So if the number is greater, you should search on the right. Otherwise, on the left. Okay, so let's see. Okay, 5, 3. So the parent is 5. 5. The number is 3. So if the number is greater, why is it searching right? If the number is less than parent data, search left. Parent left. Otherwise, parent right. I can't understand why am I doing this wrong. I think I'm so close. Searching right. Searching left recursively. So parent data is 3. Searching recursively. Found it. Return true. Return true. Why? I don't know. The log is okay. I see they found it. Let to ret equal to false. Also add return line on line 42. You are right. Let's see, Fazal. Close. No, return. Let's see. Oh, amazing. Thank you, Fazal. It was easy. Okay. Let's go. Miracle trees. Should take a break. 1 second. Okay, nice. Thank you. Nice time to talk about an important data structure, Merkle trees. As we took a look at the Ethereum data storage and as we build smart contracts, we'll often find ourselves interfacing with data structure and will be expected to understand its usefulness. Okay, tell it to me straight. What is a Merkle tree and what does it do? A Merkle tree is a data structure that allows us to make efficient verifications that data belongs in a larger set of data. They are commonly used in peer-to-peer networks. So basically, a Merkle tree that use letters for convenience. Each single letter represents a hash. The combined letters represents concatenated hashes that have been combined and hashed to form a new hash. Nice. So this is not longer, because a hash of a hash is still a hash. A hash of a concatenation of hashes is still a hash, because the length of a hash is always the same. Nice. And okay, so concatenate hit at once store the dash. Okay, yes. So let's build a Merkle tree in JavaScript. Oh my god, no. Let's see. Let's go in the implementation. So Merkle trees are awesome. They allow us to verify if a piece of data is part of a larger data structure without having all the data within that structure. This means that they can be used to check for inconsistencies in all kinds of distributed systems. Amazing. Okay, so here we have the root, A, B, C, D, A, B, C, D. In this tree, each letter represents a hash, and combined letters. But this is okay, because this is just one with one child. So if it has one child, it's the same. Okay, the rooted hash A is part of the Merkle tree. We don't need to know hash C or D. We just need to know hash CD. Nice. Let's go and implement it. Okay, we are almost at the half of the second one. So, combine two leaves. Alright, let's build as a Merkle tree. A Merkle tree will take an array of leaf nodes, combining them together 12 at a time, layer by layer, until they are reduced to a single root node. This forms a tree-like structure of hashing. Your goal, root of two leaves. First, let's write a constructor for the Merkle tree. An array of leaf nodes, a combination function used to concatenate and hash two leaves together. Okay, so take the first and second one, use the concatenate function. Here, A and B. Wait. Set the function get root on the Merkle tree. This function will find the Merkle root. Hash them together. Okay, it's like this. Okay. So we need a concatenating function. Okay, let's seek the test too. It's basically this. Hash. Okay. Just read the task again. Take the first and second leaf nodes. First and second. Okay, so it's something like that. Hash. We have to return it. Return. Hash leaves 0 plus like this. Thank you so much. Thank you so much. Thank you so much, W. Okay. I don't know if it makes sense. Maybe it's not a hash. No, hash is not defined. Maybe. So we have those const contact. Hash A plus B. Thank you so much, Sharon. Okay, so what is the task? Just concatenating? Hash them together. Hash them together. Is there a function called okay, const Merkle tree, new Merkle tree, assert equal. No, it's really hash a plus a plus b. Like it returns this. Like this. No. Okay. It's not easy. Okay, it's not getting here. Okay, let's see. We'll find the Merkle root. Hash them together. Okay. So for example, here I see, but we don't have the hash function here. Do we have the hash function? Hash. So if I do this, the hash is not defined. Okay. Okay. Okay, let's go. Okay, feel free to help here. Because so first of all we should return, because it says that it should return the hash. No. Yeah. This. But I have to define... Ah, wait. Ah, okay. I forgot. Hash. Then we have parentheses. Then we have like this. Okay. This should work. Let's see. Ah, the parentheses. No. The spaces. No. The space. Let's go. Multiple layers. So, now it's time to handle a larger Merkle tree. The tree will have multiple layers. For example, with 4 leaf nodes, you will combine the first 2 nodes and then you'll combine the last 2 nodes. Then you'll take the 2 results and combine them to get the root node. Okay. Update the getRoot function to handle Merkle trees with more than 2 leaf nodes. When breaking down the logic of Merkle trees, first we hash together A and B, then we hash together C and D, then we hash together the combination of A and B with the combination of C and D. Initially we need to combine, okay. Const layer 1 so we can do this. Let's see. Okay. Until we reach a layer with just a single element. Okay, Mida. There are several ways to approach writing this algorithm. Between recursion and iteration, the recursion is more elegant. Okay. Okay. Okay, there is this hash. Should concatenate this hash. Okay. Okay. So let's see what we get here. Implement of course we'll try to understand what's going on. For now it's not helping so much when it's about coding. Let's see. No. There is yeah. Let's go back. Okay, so let's do this for the 8th layer. So layer 1, 2, layer 1A, 1B, this is the C, this is the D, 4, 5, 6, 7, and then console.log. We need to go step by step because otherwise layer 1A, this should be enough. Okay, base case. Okay, thank you, Nehad. I doing this. This is the second day we are at the Ethereum Bootcamp. So I haven't done much Ethereum so much, but it's okay. I think if let's do this. Let's try to solve this. If leaves.length is equal to 1, return yes, we are crossed the half. No. I still can't see the hash to equal to A. So without the hash. Now why without the hash? Let's see. Okay, so yeah, but I do 12 hours. It's not a race. Hash. You do this part, Nehad. Plus. I'm doing case by case. I don't like this part, this much, but going to start from some point. At least I'm doing stuff. Thank you so much, Prasant. Okay. Don't like this solution for now. But I start seeing something. Hash, and here I can put something like that. Oi. So I'm starting to see the structure. No, we don't have it. Oh no, yes. Hash undefined. Okay. 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 You're right. Expected hash undefined. this. Okay. Okay. Expected hash. It's correct. It's correct. It's correct. Because in the case it's 4. It doesn't execute this part, so it makes sense. Makes sense. Okay. Okay. I'm getting there. Two plus b hash a plus b plus. I start seeing something. No. Okay. Hash a plus b plus hash is the same. C plus okay. Okay. This is not the right implementation, but at least we are reaching to some level. I should make this bigger. Okay, thank you. The problem is that it's Alchemy is white themed. Okay. So what's here? How should it look like? It should be hash. Okay. So this is correct. Return the hash of this. So first of all, I need 4 levels. So this is 3, 3b, 3c, 3d, 4, 5, 6, and 7. So we need okay. 3, 3b, 3C, 3D. So this is what I mean. It's a way to start. Expected hash a plus b hash. You have hash. It's correct. Something like this. It's a bit long. What is this? So this is hash of hash it's crazy. Hash a plus b plus hash c b plus here there is a parenthesis plus okay hash okay hash ef plus hash g plus h. Let's go. Okay, nice. Okay, we made it. It's not a recursive implementation, but we are getting the idea. Because they asked for a 3 level, so probably this was the right stage. Okay. Even though those trees happen to be a bit odd, your goal, handle odd number of leaves. This implementation is very poor. Okay, let's consider what happens in the case of an odd number of leaves. Because here I put case by case. Let's see. Maybe I can put this a bit here. Okay. Because in this case, let's see how many do we have here. Okay. Okay. And okay, let's see. What if we make a for loop for the leaves. Wait. What if we make a for loop for the leaves? And every time for that I equals 0, I plus plus I minus console.log leaves I. No, what did I do? This. Okay, ACE. Okay, so this makes sense. So I'm taking only the odd number. Final. So return final. Ah, there is no. Okay, so in the case of so I think this is the base case, so this might still make sense, maybe. So this is the base case. Okay. So this is the base case. I think I should eat something. Expected hash to be equal. Okay. Plus equal. Okay. No. What is this? Okay. Let's see. Probably cooking something. Okay. So this, but we need the concatenation. Okay. Okay, we missed this part. Okay. So, if the length is 1, we will return this. Okay. We needed the concept of layers, I think. Let's see. Yeah, Deepa. It's 12 hours. I've gone for 7 hours, so some support would be nice. No truth and fastest and telling true. It's come true. Okay, so Merkle layer, 3 layer. Okay, let's remove this. So let's try to have this concept of having 1, 2, 3 layers. Okay, so we have the 4. We need the concept of left and right. So let's leave this. Okay, so console log. So we log the leaf. Left and right, left and right. Let's try to use this concept of left and right. So const left node, this, because we start from 0, so the first one is a left one, right? And then we have the right. This is I, not 0. I plus 1. Okay, so this is the right one. So if the right one doesn't exist, So if the right one doesn't exist, if right node is equal to null, we just push on the layer, we push just the left one, we push the left node, we push the left node. Otherwise it means that the right one, it exists. We push let concatenation is equal to this concat the left node, right node. So we concatenate these two, and then we push on the layers, three layer, we push the concatenation, and then the get root of this so we have the constructor here. So I don't know if it makes sense to pass these as parameters. So in this case, let's try this. Return this get root, not layer but tree layer. Let's see. Leaves and this. Leaves. Right node. This is not capital. Infinite loop. Okay. Okay. Let's remove this part. Okay. The concatenation is left and right. And let me log something. Console log concatenation. But this is a for loop. How can this? Because return. If leaves. Okay, we are getting this for the first two. Expect hash p to equal hash. Okay, but we are getting there. So we have the layers before. So if the right node is null, we push the left node. Otherwise, we push the concatenation of the right and the left. Okay. So we have the left node and the right node. So initialized on each recursion. I think that you are right. No. I think that we have to remove this. Left, right. Okay. You're getting close. You're very close. Might be. Oh my God. No, we went back. No, maybe it's the opposite. I should remove the this here. Not super. Oh, I made it. My God. Okay. Time for a break. My God. My God. My God. Mind blowing. Mind blowing. Oh. Oh. The link. Let's see. Build the proof. We are at 50%. Now I want to relax. No. Okay, lunch break. Be right back.
Let's have a bit of fun till I downfall. My love, if you feel like I do right now, don't say you're on the run to the other side. My love, you say you wanna try, but you never do. Sugar, there's a reason why we lose.
I need to use this form to calculate this. Cool. Okay. So, let's go. Build a proof. Alright, now it's time to build a proof that a particular leaf node exists within a Merkle tree. With this proof, we'll only want to include the necessary hashes we need to create the root hash from our target leaf node. Okay. Let's prove C is in the Merkle root. We build the path to create the root from C. So the 4 hashes in use here are A, B, C, D, E. Since we are starting with C, we won't need it in the proof. Also, we need to know the order in which they should be combined. Okay. Get proof method. The function will take in an index of a leaf node. Index. Proof equal return proof. Okay. That's a proof. I'm just avoid dumb mistakes. Let. Okay. Okay. We're getting mistakes.
No, va bene, io preferisco.
Ok. Ok. Okay, what were we doing here? Good proof. This function will take an index. The marker proof will be an array of values with the property data and left. Data array of objects. So we need okay, so so we have the proof and we need maybe I need a structure. So we need the sort of this sort of object. So we need some point to push this object. Left and data. Something similar to this. Going well, Produma, but it's more data structure and JavaScript than Ethereum Bootcamp. But I mean, we are at 50%. Twitter down. No. Okay, leaves. Get proof. Okay. Leaves is not defined. What do you mean? This. Buffer. Okay. 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 Console log this dot get root. Okay. Okay, let's see. Let's start with the base case. So if so let's declare this. So Ctrl X, return. We can return an empty array in this case. Let's see. No. This. No. So the proof let's see. Get proof. Not easy. Hey, Krupali. So we have the base case. We always increment it by 2. Let's see. I have a kind of tough one here. So we have index. So let's define. Let's go step by step. So let's go with the I'm pretty sure that we need something like that, like a for loop when we cycle all of them. So okay, so maybe we need an additional array as a support, and okay. We need to update our get root to store all hashes of each layer. Update. Why do you want to update the get root? I think we need to do something similar to what we did before. So we need something on the left, something on the right. So so we need this left node, right node, something like this. So let's start from this. Left and right. So we have this. So this, and if there is not right, if right is equal to null, we just okay. In this case, we just push the left. The support is this one. Push the left node. Right node, we just push. Okay. If right node, support, we push only the left. Otherwise, we push the concatenation. Something like that. We create a concatenation, and with this also to remove if it's the same, if it has the we need also to remove the if it's the node, it's the index, it's included. So we also have to remove the. So before we push, let concatenation. So let's create a concatenation on left and right. And then we push the concatenation. Let's run the test and see if we did something right. No. Okay. left node, right node. Maybe we need to add this like this. So we are changing the same. So here now we can just type leaves without the this. Okay, you're not really helping the error here. Currently, our get root calculate the hashes of each layer, but forget the hash of previous one. We need to store in some array. We need to store in some array. We have this, but we can get it maybe later. Left, right. If right node is null, 3 layer we push the left. Otherwise we just push the concatenation between No, I think this is not correct. No, this is correct. Return proof. But this is like a recursive method. We can just return a recursive method. So we return the get proof. And now we need to let's log here. Console.log one is here. Support. You see, here is the support. A B C D E F G H I J. Avi. Let's go. Okay. Let's see. One second. Okay. Okay. Let's see. Build the proof. That's fair. Get proof. So support, it's an empty. Layer length. I need to go layer by layer here, not leaves. I need to go layer by layer here, not layer, but this is layer, 3 layer. So I need to go layer by layer. Layer. Let's see. Okay, now it's empty. 3 layer. Right. No. Okay. The proof, we need the leaves. Layer. Layer. With a new layer based on the leaves. Base case. So here, if layer dot length is equal to 1, there's only one test here. Okay, so if the layer is length is equal to 1, we return the empty array. Now left, right. If is not right, we push just the left one on the 3 layer. Okay. The problem is that This layer is empty. No, wait. This is not leaves. Layer I. Where is the... Let's... okay. Let's log the elements. Okay. I see a buffer here. Leaves. It doesn't like this. So this is like all layer. Okay. A, B, C, D, E, F, G, H, I, J. One second. I think that I'll take a break now because it's 3 p.m. and I didn't eat much. Okay, so let's stop first of all. Second, let's me go in. Okay, we're officially on a break. Let me check here. Okay. Okay, so I have this. I don't know if you can see it. Then I have rice with eggs. Oh no, it's transparent because it's yellow. And then I have some bonus. This is to get used to Christmas. Okay, this is from part of Julia's parents. Okay. Nice. One second. Later. Okay. 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 I'm on a break. Nice. How's it going? Impression on this tutorial. It's not much focused on on the Ethereum. It's I don't know. I have to see next weeks.
Nightmares creep while you and me repeat. This bittersweet heat is suffocating. I'm waiting and always hesitating. Kryptonite desires set my heart afire. Heart on fire. Set my heart afire.
Fazal, did you publish any of these solutions somewhere or not?
With crimson secrets and forbidden bliss, can't stay still, don't stop that thrill. My bones crave your skin, temptation within, mistakes ignite the silence. Nightmares creep while you and me repeat. This bittersweet heat is suffocating. I'm waiting and always hesitating. Kryptonite desires set my heart afire. Heart on fire. Set my heart afire.
No. No, that's a good idea. If you have the solution, we can also see this together. For me, my goal is just to have a look of the tutorial now. I struggled a lot with algorithm, of course, in the past, in the university. Oh. Oh. I'm enjoying the part of the trees. Did you do this all alone, no, Fazal? I'll sing now, but as you want. This is Twitter down. Be right back. Let's do it. Take one of these. I deserved it. There we go. Okay, so let's go. Thank you so much, Julia. Thank you. Thank you. I'm lucky. We are not using the index because the index will use it later. We need to push, not the concatenation. Okay, so we need basically this layer to push the concatenation. Okay. And then here so if push the right one, let's put a log here. Let's run the test. Concatenating something. So here we have the 3 layer. And now let's log I. And now let's run the test and let's see if they are the same, 0 0 to 0. So we want to remove, so if I is equal to index, we should check if it's the left. Oh, okay. Is left. Okay, here's something. And then push. So let object to push. We need an object to push, and this object is basically as data, and then it has left is left. Okay. So we should define is left because it's true or false. So if is left if this is right. But there is one left and one right. So it's like the index reminder 2. Let's put a console log here. Console log is left. Is left. Good night, Avi. Thank you. It's a tree. So is left, console log is left, and data is let's put it here for now because I don't understand. And now proof dot push object to push is this one. Gali. Okay, and then let's do console.log proof. Oh my god. Awesome. It didn't like this. But I'm pushing an object. What do you want? Because I have already something called left. Oh. Just have to push the object directly. Don't think so. Ah, the comma. Okay. Concatenate is left 0 data AI. Comma is missing. Thank you, Vasal. Thank you. I know that you are taking care of me. Thank you. Okay. It's very hard to fix this. Console log is left 0. But this should be a boolean. This should be a boolean. Maybe double false is left false. Is this bootcamp paid? No, it's not paid, but you need an invitation. So, okay. It's very hard to control this. So, okay. Leaves. Okay. So, this is 3-layer. But see here, I don't use the index, but I put it here. If index, it doesn't like it. Why? I don't understand. So, if for layer length I plus 2, then we have this console log. We have the left node and right node layer. This should be no, let's put left and right here, because maybe I want to return, because I need to call it recursively. I think at some point I should return something recursively. So this is very hard. I'm gonna do it anyway. So left, right, if let's put a console log here. Left is left, right left is and right is, but why are they buffers? Left node, no, left, right. It's very complicated. The list argument buffer JavaScript, because it's I really can't debug this. It's very hard. Data, Fasal, if you can, if you know the line, just put the line if you can. Okay, so let's see. I think we need to is left proof push. And at the end we need to pass the proof here. Because this is a recursive method, so we need to pass the proof in every iteration. And then at the end we can return this get proof something. Math floor. We need, I don't know if this is enough. Index. So we need to get proof. So this is the index. This is the index, the layer, which is 3 layer, and the proof. I don't understand what's written here. 3 layer is not defined. It's just a layer. It's layer. Layer. Now here I am using, wait. Just put the layer here, just put the layer, let's try this. Okay. Layer, get proof, math floor, index and proof, new layer. We need support layer, const support layer, because I need I don't know what's wrong with my keyboard. But the layer that we use here because we have the layer and we need an additional layer for the support. Right, I don't know if it should be here or outside. And here when we do the push is probably here. When we push it, it's in the new one. It's very hard. I can't understand. Left node, shift 2. This is left. But we are getting look how much I logged. Data will be index plus when if it's even But I think that we are getting very, very close. Data. The data. But here, this is wrong. Of course. Is left. This is. Is left false. Data. Because is left. Console dot log is left. No, it is left. They're gone now. Is left true. Right. Right. Let's log right. So dog right. In the right there is the buffer. So we can if catenary operator. Catenary operator is left. In this case, return this part. Otherwise, this. Oh my god. No. I crashed it. No, this is okay, let's see some help now. For calculating the proof, we need to pre-calculate. We need pre-calculated hashes. So we need to first update the get root. I'm trying with this this way now. Tom, thank you, Rongali. In your case, the logic you're trying to in else need to move it after the for loop. Thank you, Rongali. After the for loop. Let's see. Let's remove this. Left is left. Is left. Maybe qua we can do a console.log with object.push. Object to push. But there is something that is breaking the... No, I don't know what it is. Return get proof. Const emulator. Const support layer. Else if left is left index I keep missing this semicolon. Okay. If I push not just right or just left, we have a different error. Is left true? Is left true? Left false? Left false? The data is the buffer. Wow, look how many logs. We have this here. I know that we are not that far. Is left is true. Right, we have right. Is left. So it's true that the first one is left. So data const to data equal to if is left to data equal to of course is to data equal to, but const to data 69. Let here it says left false. It should be left true. I will have a hashes to proof. In case of event. What do you mean in case of event, Fazal? Then data will be support. What do you mean? Support index +1. If I is index or floor index support layer proof. Yeah, just put some link, but I think we are close because we are logging a lot of stuff, but we don't have support from the logging because of the testing. I don't know. It's what it is. No, I can't even log it. But the problem is that I would like to go with this part. So maybe if you can, if you want to to keep going in this part is okay, otherwise I'll just keep going on this part. To data, let's do data. I don't understand why it always go in infinite loop. It crashes. Let's see. I think we're not very far, but I don't know. Get proof. So we have index, layer, proof. Okay, if the length is 1, we just return the empty part. Does it make sense? We just return the proof because we are reducing. My god. I can't even test it. This. Okay. So if layer length is 1, return the proof. Const support layer, and now a for loop. So 0 layer length e plus equal to, then we have left and right. Left is layer I and right is layer I plus 1. Now if it's not right, we push the left part. If it's not right, we push to the left one. Otherwise, because on the right we should remove in case we I think we are not very close, we are not very far. Support push. So we push concatenating, and then if I is the index or I is the index minus 1, proof push. Is left. Proof push. If it's is it left, then push the right part, otherwise the left part. No, what is this? Oh! I solved it! It's done. Oh my god. Okay, this has been the hardest challenge I made so far. Good night. Oh my god. Fuck. Oh. Okay. Reward. Oh. Almost done. Remember that proof that we just made in the last stage? I remember it pretty well. Take the node and combine it with all the data provided in the proof. This to the true root. Return. Proof. If you up to own your own. Proof. Oh, it's still logging stuff here. Hey Farok. That's okay. Hard part has been done. I can't understand. Let me. Okay. Hash, hash, hash. What do they mean? What does it mean? Okay. Okay. Let's do 4. Let I equal to 0. I plus plus. I plus plus, sorry. And proof. So this is a for loop. We need to check in case of if there is the left part or not. So if else and then we have a return. That's aux. Let's use an auxiliary variable. Hey Xavon, how's it going? And here we should triple check aux with the node. If the proof, the index of the proof, let's do a console log. Okay, so if on the left part, then this auxiliary variable is do we have concat here? Can we concatenate the proof? Proof.data, proof.aux, no, proof.data. Oh no, the proof are data is left. So here is okay. So concatenate basically, okay, one is already there. And in this case, we need to concatenate the opposite because the order matters. So here is data with this. Oh, here is the root. Let's see. Data is not defined. And this is aux. Let's go. Data is not defined. No. Data aux. Let's go, let's go. No. Cannot read the property left of undefined. Undefined. Where we have the proof? The proof is the left side or not? I don't know. Proof. If console it's okay. Console log proof. Proof I. No, but here is proof I undefined. Undefined. How can it be undefined? Yes. No. But it's not this in JavaScript. Why? Maybe prof length the -1? -1? Why the last one is undefined? Wow. Don't have Control Z. Like this. I don't know. It's undefined. Concact. Here it says in line 9. I don't know what to do here. Let's see. You see, it's not on line 10, it's on line 9. Ah, sorry. It's not on line 10, it's on line 9. Because, how can I say? The property of undefined in JavaScript, the trick. Almost did it. Ah, Fazal! Yes! Yes! Amazing. Now there is this one. It seems easier, but I just have to check. We just have to check to avoid. Can't remember the syntax now. Yeah, oh my god. Oh. Okay, I'm getting tired. Why was it working so well? Okay, thank you so much. Thank you. Okay. Nice. I just lost my computer science degree, like that. Okay. Merkle trees, and I'm not watching this video. Merkle trees in Bitcoin. Okay, here is explain some stuff. Someone, you saved the day. You saved the day. Someone saved the day. Take a screenshot. I can't believe this. How was it working so well? Okay, I'm not reading this part. But I already read this. Merkle trees. Patricia Merkle trees. Okay, Bitcoin was the first blockchain-based decentralized network ever. It popularized the use of Merkle trees for scalable transactions inclusion. Ethereum also uses Merkle trees, but since Ethereum is completely different design, it also uses one other important tree data structure for some of its data storage needs, Patricia Merkle trees. This is the last data structure heavy day. It has been just one day. If you've made it with this far, you're doing fantastic. Patricia Merkle trees are the first introduction into Ethereum, specific fundamental.
Let's do it.
Okay. In the previous section, we covered how Merkle trees are used to efficiently record a large amount of transactions into blocks. Ethereum block architecture. Bitcoin architecture is simple. It's a ledger that keeps track of transactions using a UTXO model. Since Ethereum keeps track of a larger amount of state data, the block architecture is completely different. Okay. Why are you showing me block architectures? Aren't we covering trees? Well, because this blocks contains references to the tree data structures you are focused on. Okay. The main goal here of showing the block architecture first is, by the end of this lesson, you should be familiar with 3 of the staple Ethereum block properties included in the diagram above: state root, transaction root, receipt root. Okay. Just like in the last section, we covered what the Merkle root hash was in the context of a Bitcoin block. We will now look at 3 new similar trees uses in Ethereum. Okay. Review. Merkle 3 in Bitcoin. I don't know why it was working. and yeah, and the IDE was not correcting. I wrote this very fast. It's work but infinite. But it was not. But it was not looping infinite. It was looping infinite. It would have been in the first place when I went to check. Okay, radix tree. Okay, radix tree is a tree-like data structure that is used to retrieve a string value by traversing down a branch of nodes that store associated references that together lead to the end value that can be returned. Okay. Okay, what is a Merkle Patricia tree? I'm here. It's an acronym. Data structure stores key value pairs, just like a hash table. Patricia is a particle algorithm to retrieve information coded in alphanumeric. Okay. I didn't know this. Why does Ethereum use a Merkle Patricia tree? There are typical 2 different types of data, permanent and ephemeral. Permanent. Once a transaction occurs, that record is sealed forever. This means that once you locate a transaction in a block transaction tree, you can return to the same path over and over to retrieve the same result. Ephemeral. In the case of Ethereum, account states change all the time. A user receives some Ether. Hey there. It makes sense that permanent data like money transactions and ephemeral data like Ethereum accounts, balance nodes should be stored separately. Merkle trees again are perfect for permanent data. PMTs are perfect for ephemeral data, which Ethereum is plenty supply of. Okay. Ethereum block header. The block header contains many pieces of data. Remember back to week 1? Yes, because I made this today. The block header is the hash result of all the data or the elements contained in a block. It's kind of like the gift wrap of all the block data, which is perfect for Christmas. If you look at the Ethereum architecture diagram at the beginning of this lesson, the block header ends up hashing all of the data properties of the block. It also includes state root, the root hash of the state tree, transaction root, the root hash of the block's transaction, receipt root. So state, transaction, and receipt. As shown in the above diagram, the state tree acts as a mapping between addresses and account states. It can be seen as a global state that is constantly updated by transaction executions. The Ethereum network is a decentralized computer, and a state tree is considered a hard drive. All the information about accounts are stored in the world state tree, and you can retrieve information by querying it. Okay, let's go. Account example. As mentioned above, the state tree is just a mapping that uses an address as the key and the account state as the value returned. Balance nonce root code hash. Okay. Just 2 hours and a half. Let's go. Xavon is dev. Xavon is dev. I noticed it now. Xavon, why do you have different names? Oh my god. Transaction examples, okay. Ethereum transaction received 3. Okay. Nice schemas. Okay, let's just read this. Conclusion. The above diagram is an excellent visualization into how the trees all end up being committed in every block via their root hash. The raw data is stored elsewhere in Ethereum. Take a look back over the various architecture included in this lesson. Does the Ethereum block architecture diagram look less threatening? If so, good. We're learning and we go as we go, and we've just covered some of the lowest level aspects of Ethereum data storage. Very few people learn these fundamentals. These are super important. Not only does learning them give you a more holistic understanding of Ethereum, this is knowledge applicable in all of computer science and even physics. The important takeaway of this lesson is to understand why the low-level data structure used by Ethereum are used to optimize data space and read-write efficiency. I liked this approach. It's a bit hard. Helipad Lormit. Actually, it's pronounced like try. Okay, try. This particular data structure works well with storing strings, especially one with many common prefixes. Let's look at a try. This try contains 3 words. Helipad, hello, hermit. To figure out why, simply follow the arrows. All 3 words starts with he, so this prefix is shared. After that we branch out to hermit and L for both hello and helipad. Let's build a structure to learn more about it. A new data structure, okay. Let's go. So I need one more lesson for sure. It takes some time, but for example today I made almost 2 lessons, so I'm going faster. Maybe. We're going to create 2 data structures for the first stage, the tree and tree node. Okay, tree node. The tree will represent the entire data structure. The tree node will represent each letter. Tree node, okay, is a letter. Okay. Key. This key equal key, then we have these children equal empty object, false by default. It says 4 properties. Key, children is word. Okay. This root equal okay, let's try. Tree node is not defined. I spelled it. It said 4, but they are 3. Okay. Let's focus on the example from the previous stage. To create this tree, we will simply do this. Thank you, Dev. Try equal new try. Try.insert hey. In fact, if you look at the test cases, that's actually what it does. Okay. Add a new function called insert. This function will take a string word. Split this word by character. Split word in JavaScript. I think it's word dot split word. This one. Okay. Console.log my array. Okay. And now okay. Split. Yes, split. Yes, we can. Create nodes. New tree node. Running true. adding a function called insert on the try class. We take a string word, split this word after create nodes. Create nodes. Hey Vivek, thank you. New member. It also looks very nice. Nice. I have 3 members videos so far. I also sometimes I post some very exclusive content for members. Okay. Only the last. I don't know how to do this. Cannot read property key. Thank you, Vivek. Let's go. 3 months together, Vivek. Thank you. Nice. Now you have the exclusive Francesco Semacis. Your life will no more be the same after this. Nice. Okay, so let's go back here. What is it? I lost it. Let's go here. Let's do another for loop. I minus the word dot length I plus plus so if is the end, if I is equal to word dot length, so it's the end. It's 3, yes, minus 1. Okay, is word equal to true. Okay. So we can do node. This is let node okay. Insert a word. But we needed the split word length. Can I do the word? Can I do a for loop? Can I do a for loop like this? Hey, Vivek. Nice. You have to create a new function called insert. You are right. Where am I? But we are in the tree node. I was doing some... Oh my god. Let's go here. Okay, so the problem here is that I can't reset. I don't know why it's... So we insert a word, weird word. So we say that the word dot split word array. Not using IDs anymore. Okay, now let's do a for loop. Let I equal to 0, I minus the word array dot length I plus plus console dot log Oh. Why? Okay, or the array is not. Okay. Okay, nice. Nice. Now we need to create so if I is equal to word I mean, it could also be y, but no, let's stop this. But here we are missing something. This root equal to new tree. So we need to initialize the tree node. So create the node. Okay. Okay, so let node equal to this root at the beginning. And so the node children, node children is an object. Is an object. Word like this. The key, the children is HH, so it's the same. Word I is word array I. Word array I equal to new tree node with as a key it has this. And the node is equal to node.children word I. Word I is this element. Oh, awesome work on that one. It's worth a try. Sorry. Julia. Nice. I'm a bit tired today. Today I'll just do 12 hours. Today I'm really struggling. Ooh. Okay. Let's go on the next one. Insert branching. I want to finish this, but I don't know if I can do it. But still close. Let's see. Okay. Now. Now, branching. An important aspect of the trie is its ability to branch and have many children. Interesting. Okay, put the letter E and the first L will have two children. The data for the E would be okay, so a children is an object, it's not an array, but it's an object of elements. Okay. Implement branching. Oh my god. Depending on how you implemented your logic in the previous stage, you may already be passing the test cases. So, first of all, let's remove stuff. I created a new try node. So this might work. Let's see. No. But we're already very close. Node children word. Node children word I equal to new try word console log. So let node equal to this root 4. Okay, but we are already passing many. Connect the final letter. Connect. It's missing something. I word dot length. Okay, so I think we need to add a check here. We have node children word array. If it's not already a children. Is only if node dot children word I but we are very close. Oh, made it. Is it not really a word? Oh, I'm suffering. Does it contains the word? Does it contains the word? With a try, we should be able to quickly figure out if the data structure contains a word we are looking for. Okay, okay. For example, if we were to add a few words, happy, healthy. Okay, interesting. Okay, check these words. Okay, true, happy, healthy. The second one is a bit tricky. Add a function contains to the tree. Okay, so contains. So contains. So okay, we have in the node we have a cool property which is word. So we should check if it has this is word. We should check if the last. We should check if the last letter has the is word. Right? So this should return something at some point. A for loop. Maybe we don't have to use the split one. Let's do this. Let I equal 0. Word. Let's see if it works. If it does work. I plus plus. We should iterate. We should iterate. We should iterate. If so here we have word I. No children. So if let's do a console log. Node return. Word is not defined. Contains word. No. Or maybe we should use the same for loop. Wow. Oh, I made the same mistake. Don't kill me. This time I noticed. This time I noticed. Node children, node children, node children. It goes infinite. Hey. So so we should iterate, so we have if node equal to this is the next step. Ah, this passed. Okay, so in this case return false. Let's go. We cannot contain our You cannot contain our excitement. Really? Okay, Merkle trees in Ethereum. Okay, let's go. Here is a technical overview of Merkling. Is this a verb? By Vitalik Buterin. Vitalik highlights several reasons for using Patricia Merkle tries in Ethereum. Efficient data verification. More complex light client queries. Thank you, Julia. Efficient data verification. More complex light client queries can quickly change values and only recompute a portion of the tree, prevent some DDoS attack vectors. There is a limit to the depth of the tree, which prevents other DDoS attack vectors. The order of the updates do not matter for the root hash. Ethereum nodes maintains 4 tries: a state try, storage try, a transaction try, a receipt try. I remember that there were 3 before: storage, transaction, and receipts. State contains information, etc. etc. Here is a good overview of Patricia Merkle trees on Medium. Okay. Quick note on RLP. What is RLP? We're going by seeing RLP come up quite a bit. This is a serialization format used in Ethereum. You can think of it like JSON. It is used to send data from one machine to another in a format where the machine knows how to parse the data. RLP. What is RLP? The link is broken. Interesting. I never made a post on this. Nice. Tomorrow I have the post. Okay, mark complete. Hey there, after going through this week's content, you may be wondering, why am I learning about trees and data storage this week? Why? Good question. The reason is that blockchains have a storage problem. They require that the nodes in the network store every value recorded in their shared database. For Ethereum, this means all account balances as well as every persistent variable. 1 second. Let's go. This is the project. So I made it. I made it. I'm not gonna do the project today for sure. Let's take a break. Let's take a coffee and then okay. So I'm not doing this for now. Weekly recap. Congrats on finishing week 2. Learning retrospective. This week we learned about Merkle trees. We'll see this amazing data. Let's go on. Let's see if it's complete. Yes, there is the week assignment, but I'm not doing this on the stream because otherwise it's too boring. Maybe I can decide maybe to do this offline or maybe show some parts. It really requires me to focus more. Okay, nice. December 8th. Oh. Let's see. Just the assignment. Let's go. UTXO model coding the UTXO model UTXO locking unlocking scripts and then data structures, and then we have blockchain data storage. Let's go. Merkle trees. Sorry. Tree data structure. Nice. I don't know why it always takes it always. Let's go. Second, let me make the Twitter post. Let's go on. Only 71 likes. I'm very disappointed. 70. 71. Very, very disappointed. 100k tweets. I've been a bit too active. No. Bam. Now coffee break. Let's go. So I will not finish this, but break.
No stopping us. Fly without boarding pass. Couldn't catch me, I'll be
Let's go. Oh, let's go. Oh. Break, break, break. Okay. Oh wow, this is nice. Break, 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 break. Maybe in this one I can make it bigger. This one. What do you think? I'm taking a break, taking a coffee. Now I feel better. Wow. Ow.
Looking at a shooting star. Got more than a couple of people going mad. I
swear they're rooting hard. Tell them I'd be big in the game like she went and got them breast implants. I said I'm moving too fast, didn't even get to glance. I'm ready to eat up track like I'm seated in a restaurant. If you had swag like mine, you know it's best to flaunt. We are hating because we are shining like it's neon, rock like kings of Leon. Shooting stars across the galaxy. I stand out, so don't be mad at me. Infiltration with my strategy. When I turn up, then I just have to leave. Shooting stars across the galaxy. I stand out, so don't be mad at me. Infiltration with my strategy. When I turn up, then I just have to leave. Yeah, shoot, shoot, shoot. Yeah, shoot, shoot. Yeah, shoot, shoot. Yeah, shoot, shoot.
Focus on YouTube. But I need help. Focus on YouTube and the 4C community. These are the main focus. And of course, public speaking. One goal that I want to achieve, I already said this some couple of times. I want to achieve 1000 subscribers per month on YouTube. As you can see, good views today, but we as subscribers, I think it's going well. It could go better, but it's going better than usual. So let's see. It's not easy. With technical content, it's not easy at all, especially if you're a developer advocate and you do more stuff. But thank you for your support. Really appreciate it. Show your revenue from YouTube. You didn't say please, so I'm not gonna do it. Let's go here on the Ethereum. So, introduction to Ethereum. Review Ethereum block architecture. Block and header, block and +1 header. Previous hash, nonce, timestamp, uncle hash, list of uncle block. Okay. Okay. Not super clear, but it's okay. Of course, I'm joking, Farouk. It's doable. Not impossible. Doable, but it requires some effort, or you need a very good video. Since I don't know and I don't have any skills, I just go all in. What is Ethereum? The computer science technical definition. Ethereum is a deterministic but practically unbounded state machine consisting of a globally accessible singleton state and a virtual machine that applies change into the state. Practical definition. Open source, globally decentralized. I like the visual definition. I made a short on this. Imagine thousands of computers all over the world connected by the internet. Yeah. Very similar to the definition that I usually do. Yeah. Thank you. Thank you, Deb. Can you raise an issue, please? or tell this also on the website in the Discord server. Thank you so much. Oh, that's me. Okay, let's start a poll. No, let's put something else. I don't know. Later. Because of course if you're here, you're gonna vote yes. It's biased. Chatbot. Where is the Alchemy? I missed it. I lost it. Oh, this one. Ok. Ethereum a computer. Okay. Yeah, here there's a lot of theory about Ethereum. I've been studying this for 1 year, so I'm gonna a bit faster here. Natively multi-user, verifiable and auditable. Why? Ethereum versus Bitcoin. It's not. It's Turing complete. Proof of stake, Ethereum. Yeah. I like this. Ethereum virtual machine. Gas. Okay, here is a very good lesson. I'm going a bit fast here. Just if I see something that it's interesting, I stop. But okay, parity. Okay, here is just a very long and dense theory, so I'm gonna skip this part. I'm more focused on the coding part, of course. Oh, proof of stake. Okay, let me just. Okay. Okay, on September 15, 2022, Ethereum transitioned from proof of work to proof of stake. I did this on live on YouTube. I also made a short out of it. Hey Div, how's it going? Going well. We are on the third week. So I did 2 weeks and started the third one. This was a massive migration that was always in the roadmap and original planning for Ethereum, but required coordination from the entire network to execute. We learned about proof of work, the consensus mechanisms used to buy Bitcoin and previously Ethereum in week 1. Proof of stake is a totally different mechanism that enables Ethereum to be more secure, less energy intensive, greater scalability. Let's unpack how POS works to understand why this is the case. Okay. How POS works. In order to become a miner in proof of work, there are large energy requirements, which makes it difficult for any individual to compete with existing mining warehouses that are dedicating millions of dollars of resources to mining. However, there we go. Why, it's always a bit. Oh. The way I love the highlight feature, amazing. However, in proof of stake, I can make it a bit bigger. The energy requirements to become a validator is much lower and can be done by individuals without a high overhead energy cost. This encourages more users to become validators, decreasing the centralization risk and thereby increasing the security of the network. Instead of using mass amounts of electricity, validators are required to stake 32 ETH by depositing it into a contract to have the ability to validate blocks. This staked ETH is used as collateral against the bad actors in the network. If any given validator acts dishonest or malicious, they put themselves at risk of losing their stacked ETH. Rather than all validators competing at the same time for the next block, the network randomly selects a validator to propose a block every 12 seconds. All the other validators verify that the proposed block is correct and the cycle repeats. Okay. This means that the energy requirements to mine any given block are significantly lower than the proof of work. How proof of stake affects Ethereum development. I should have the book here. 1 second. I have this one. Proof of stake. I could have given a giveaway of this. Maybe it could have been a good idea. Let's go. Okay. Sorry. Proof of stake introduced two. Sorry. Okay. Here's an overview of all block tags. Earliest. Block tags. New levels of finality developers should consider when requesting data from the network. Safe and finalized. Okay. Okay. The most recent crypto economically secure block that has been accepted by two-thirds of the validators. Typically finalized in 2 epochs, 64 blocks. Cannot be reorged outside of manual intervention driven by community coordination. Intuitively, this block is very unlikely to be reorged. Okay. Safe. The most recent crypto economically secure block, typically safe in 1 epoch, 32 blocks, cannot be reorged outside of manual intervention driven by community coordination. Intuitively, this block is unlikely to be reorged. Latest. The most recent block in the canonical chain observed by the client. This block may be reorged out of the canonical chain even under healthy normal conditions. Intuitively, this block is the most recent block observed by the client. Pending. A sample next block built by the client on top of latest and containing the set of transactions usually taken from local mempool. Okay. Making request. Let's go. Gas on Ethereum. In the previous article, we talked about the cost of operation codes in terms of gas. In this article, we will take a look at the actual price of gas and understand what determines it. Okay. Ethereum approval proposal. Sorry. As many of you may know, the price of gas is something that changes with every block. Historically, gas prices on Ethereum have been unpredictable and at times astronomically high, making transaction inaccessible to most people. However, in August 2021, after years of research and planning, there was an Ethereum approval proposal proposed to improve the calculation of gas prices on Ethereum, Instead of covering the antiquated computation, we're just going to focus on how this works for the current state of Ethereum. If you want to learn more about the specific dynamics, check out this resource hub. Okay. Gas prices. The cost of operations on Ethereum are fixed and measured in amount of gas. We're going to understand how these prices are set so that you can be more informed about transaction costs. Ah, I didn't know about this. Ethereum gas tracker. I didn't know about this. This is a specific one. Denomination of Ether. Just like dollars, Ether has different denominations that are used to express smaller values. And so, okay, this is there are tables on this. How is the price of gas set? This is interesting because let's see if it's the same after proof of stake. So, every block has a maximum amount of gas that can be used within it. This is how the number of transactions included with a block are determined. Every block has the capacity to use 30 million gas, but has a target of 15 million gas total. The price of gas is determined by the amount of demand for transactions, where demand is measured by how filled the previous block was relative to the target gas. Okay. Interesting. Okay. The above screenshot shows two different blocks, one where block space was in high demand and another where it was in lower demand. The network first sets a base fee. In an ideal world, this base fee would result in 15 million gas getting used in a block, no more, no less. However, what happens in practice is the actual gas can be above or below the target gas. When blocks are above the target, the gas price or base fee is automatically increased. Increase the cost and barrier to entry for sending transactions and thereby reducing the number of people who are competing to fill the block. When the block is below the target, the base fee is lower to incentivize people to transact by lowering the barrier to entry for paying for a transaction. The base fee helps users select an efficient gas amount that is likely to get their transaction mined rather than wasting tons of money on unnecessarily high gas prices like we've seen in the past. Okay. We can see that we are 57 below the desired gas target. Okay. Only using 66.4 million gas instead of 15 millions. What do we think will happen with the next block? No, I don't know, we don't know. We can see that the base fee decreased to 11 GUI, and by doing so, this incentivized more people to send transactions and the gas used skyrocketed up to almost 30 million, 100% above the gas target. Now, what do we think will happen with the block 16, 12, 89, 23? Let's see. 43. Okay, decreases. This prevents the miner, but this is stake. Proof of stake. Should check this. Anyway. Okay, so how are miners paid? Since the base fee is entirely burned, the new incentive for miners is now known as the miner tip. In a perfect world, the miner tip is the minimum amount that the miner is willing to accept in order to execute your transaction. This tip was originally set as 1 GUI but can fluctuate depending on how full blocks are. Since the target gas value in blocks is 15 million, in general, so long as blocks are hitting or near the target amount, there will always be room and more transactions within a block. This is why the miner tip doesn't need to be insanely high to get your transaction included. Typically, when you set the gas for your transaction, you are setting up a value called max priority fee, which is equal to the max fee plus the miner tip. We learn more about sending transaction. Hey Mars, thanks you go. Thanks you go. Appreciated. Did we reach 1,100 likes? Let's go. Let's do it. 74. Let's go. Okay. Oh. Okay, let's go. Transaction game. Activity requirements. Apex Wallet, browser extension wallet that provides key storage and secure account login, allows you to send transaction and act as a JSON RPC gateway. We'll be using Apex in these instructions, but feel free to use any other browser-based wallet. Alchemy University Discord, community of thousands of students together. We'll be using the AU Discord to make friends and send test Ether for this activity. Okay. Setup. Install. Wait, we are 1 hour. Install the Apex wallet. So for this activity, we'll use our wallet to connect to a test network on Ethereum. If you haven't already installed a wallet, you can install the Apex wallet for free by following this instruction. Okay. It's true. I don't know why they are not recommending MetaMask, but Apex wallet. Why? Let's go. Let me do this offline. One second, I'm copying the seed phrase. Okay. I should be, by the way, I will delete this wallet in any case, so. Let's go. I lost myself. I lost it. Ah, there we go. Okay, so install the Apex wallet. Create separate browser account. Okay. Toggle to girly test network. Okay. I like the interface of this Apex wallet. Yep. Acquire Gorley Ethereum. Okay, I have the Alchemy account. So let's go here. Or is the copy address? A faucet. What is this? I don't know what's going on here. Okay, nice. Okay, nice. How to send a transaction in your wallet? Now toggle the Gorley. Select send. In the address event, copy paste the public. Okay, here is the same as MetaMask, nothing strange. Game description. Okay. I can't find it. Announcement. I can't find it. Bah. Okay. Transaction activity. Let me try. It's not working. Okay. Scroll through this channel to see some other facts. Do you know about this this thing? Transaction activity, post your address. Hey Efrain. Okay, no problem, let's go. Ethereum accounts. There are two types of accounts in Ethereum: external owned account and contract account. I made some tips already on this. So externally owned accounts. External owned accounts are similar to Bitcoin private public key pairs. In both models, the addressed and published key are associated to a private key via an elliptic curve digital signature. Wait. However, the method to get from a private key to an address in Ethereum is different than Bitcoin. The resulting address in Ethereum is a 40 characters hexadecimal string as opposed to a 26 to 35 alphanumeric string in Bitcoin. The biggest difference between EOAs and Bitcoin's addresses is the EOAs have a balance. This means that the global state of the blockchain actively tracks how much Ether every active address on the network holds. Minor clarification. An active address refers to an address that has interacted on the Ethereum blockchain. There are technically possible Ethereum addresses. Those addresses are not included in the global state tree until they have interacted with the blockchain. Okay. Now, accounts versus UTXOs. To transfer value in Bitcoin, we spend UTXOs. In Ethereum, there are no UTXOs. Instead, at the end of a transaction transferring Ether, the transferred amount is subtracted from the sender's address balance and added to a recipient address balance in the global state tree. Okay. Compared to UTXOs, an account balance is quite straightforward, especially from an application developer perspective. The EVM has an operation balance that allows us to look up an address's balance inside code running on the Ethereum virtual machine. Okay. Okay. Compared to UTXOs, an account balance is quite straightforward, especially from an application developer perspective. The EVM has an operation balance that allows us to look up an address's balance inside the code running on the EVM. This is much simpler than adding all unspent transaction outputs that have a particular address as their recipient. Okay, let's go. Let's go. So let's say that you have 2 Ether in your account and you want to send 1 Ether to Bob. You'll be able to broadcast this transaction to the network once you sign with your private key. Okay, nothing. Let's go. A little bit more practice, please. Smart contracts. Okay, let's read this part. Contract accounts. Finally, we broach the most exciting part of Ethereum. Finally. The term smart contracts sound pretty intimidating. No. Don't worry about the name. It's simply a program that it's a bit smart. As a developer, that's grifting. Alchemy grifting on their page. Pain. I'm preparing this because I'll post it later as a developer. Okay. Once you've completed the code, you can deploy the contract on Rust. You can do so by running a transaction from your externally owned account with the bytecode of the compiled smart contract. This contract has its own account in that it also has a balance and address. The contract account cannot be controlled by private key like EOA. Instead, EOAs makes transactions to call functions on the contract. From there, contracts can also make calls to other contracts synchronously. Once a contract is deployed, the code cannot be changed. However, the storage of a contract can be updated through transactions. Okay, nice. Let's go. In this article, we discussed both types of account on Ethereum: eternally owned account or contract accounts. Perfect. will I ever write some Solidity code here in this bootcamp? Supplemental reading. We covered a whole lot in this section. We are here are a few additional resources for you to go through in depth on topic we discussed or learn about totally new areas we didn't cover. Okay, the history of Ethereum, I'm gonna skip it. Node clients, it's crucial aspect, having a diverse set of clients reduces the factor. Yes, sometimes I post about this. Ethereum mainnet statistics. They are trying to have as diversified as possible. To be honest, it's not really diversified, but compared to 1 year ago, it's going better. Since we are using Alchemy for our deployment, we don't need to worry about which node to client. That's seriously? No, it's of course I am on the Alchemy tutorial. It will be disrespectful to use another node. Nice. And let's see, here they have you know what to do. I'll skip the history part. Ultrasound money, what is? As we learned in the gas on Ethereum section, Ether is now burned after transactions are included in blocks. One day I'll play a game online. That's for man. I forgot to put the glasses on again. Okay. What is ultrasound money? Okay. If you're taking this course, you're probably well aware of all the potential use cases of Ethereum. Here are a few that are helpful to understand. Ownership records, code, other popular areas, other resources. One day I'll be here too. Nice. Intro to JSON RPC. Okay, I would like to write some code, but okay. Intro. Ethereum is simple, a computer for all intent and purposes. The main difference is that the single computer is spread out over thousands of nodes worldwide. A JSON RPC is the way Ethereum can communicate with another Ethereum computer, basically. I bet Vito drew this. Don't see the nice. The image is a super simplified. I don't know, it's funny. Core concept, Ethereum clients. To run an Ethereum node, you must run one of the various Ethereum client implementations. You will see there are quite a few, including Jet, Aragon, and Nethermind. Okay. Here is some more information. I think that today I'll stop a bit earlier because I want to plan the next challenge, the possibilities, the tutorials. I want to lecture, learn web 3 DAO, so I want to check. And they're releasing this once every week. So since I made basically a tick 2.5, maybe I can make Alchemy once every 2 months, I think. Maybe too much, not too much. I should make another one on January. Maybe. Maybe I can make the next one on January about Alchemy. Okay, let's see. Let's see. Because I also would like to go back to learn web 3 DAO. Let's see. I'll probably make also a poll. JSON RPC is a remote procedure call protocol that uses JSON to encode messages. Okay. It's a standard, exactly. Block number, get balance, get block by number, send root transaction. Perfect. For example, we don't have the edit tweet. We don't have the edit tweet. One day we will have Twitter Blue and I'll edit my tweets. I don't know if I'll reach 100k tweets before or we'll have the edit button. Okay, this is Miley. Apex Wallet. They're getting fun. They like Apex Wallet. Okay. Okay, this is JSON RPC response, JSON RPC tools. The Alchemy Composer. This is nice. But is this for everyone or just on my channel? Do you like this? This is harder than it looks. It looks easy to implement, but it's not. It required some effort. But now we have it. So Alchemy Composer, let me save this. Conclusion. Thanks to every Ethereum node containing a JSON RPC interface, we can communicate with the Ethereum blockchain in an instant. Cool. Read, write, Ethereum, transactions. Okay. Let's go. Let's go. Set up an Alchemy account. I already have an Alchemy account. What do you think you're talking about? Let's go. JSON RPC reader requests. The time has come to set up an Alchemy account. Congrats, Web3. But I really appreciate that they put this just on the third week, not on the week one. I really appreciate this. Nice. Okay. Okay, I already have done this. Follow the steps below and check out how this video is set up with the RPC URL. I already done this multiple times. Okay. I've already done this, so I'm gonna skip this part. Install Axios. Giulia. Okay. I don't want to do this part. I've done this multiple times. It's basically an Axios request. I made various tutorials. I'm gonna skip this part. It's very easy. Axios request. No, I'm gonna skip this part. Okay. Ethereum nodes are what maintain the integrity and data on the network. There are several different types of Ethereum nodes that are participating in the network and are used depending on what type of data is needed. Full nodes store and validate all blocks and transactions over the entire blockchain locally. When a smart contract transaction is executed, Ethereum full nodes execute all of the instructions in the smart contract. Together, full nodes determine whether the smart contract execution is producing the desired result. However, running full Ethereum nodes is expensive too, and can consume a great deal of energy. Luckily, Alchemy provides access to all archived data and the latest data. completely for free. Okay. In the below video, we will break down how nodes work, what they can be extremely challenging for application at scale, and how to solve data consistency issues. Ethereum, this image is a bit blurred. It's blurred because I have YouTube low resolution. Bonus material, data storage. We've talked about Ethereum nodes storing information locally, although we haven't really talked about how they store the data locally. Let's take a closer look. State try, storage try, transaction try, recipes try. Okay. Okay, we discussed the potential issues you might run into with Ethereum nodes and how data is stored on full nodes, which is admittedly pretty intense. Much of the Ethereum system is designed around incentives on how these nodes are able to store and validate transactions, so this is an important thing to keep in mind. An upcoming session will be moving more high level. We'll start to interact with these nodes using our Alchemy endpoint and learn the user libraries to make our lives easier as developers. Transactions. I want to code. It's good, but a bit boring. Okay. Okay. Write the state. Ethereum, a transaction-based state machine. First of all, let's get it straight. The Ethereum compute is a fly. Okay. The vehicle to, okay, first of all, let's get it straight. Just move a bit so I don't stay always in the same position. Okay. Better. First of all, let's get it straight. The Ethereum computer lives and breathes transactions. They are the only vehicles that can actually change any state in the computer, as shown in the diagram below. Okay, Ethereum can be viewed as a transaction-based state machine. What is a transaction? Ethereum. An Ethereum transaction refers to an action initiated by E. I'm sorry. EOA. Sorry. In other words, an account managed by a human, not a contract. For example, if Bob sends Alice 1 Ethereum, Alice is happy for sure. Thank you, Salman. Thank you so much, Salman. An Ethereum transaction refers to an action initiated by an EOA, in other words, an account managed by a human. Okay, for example, this state-changing action takes place within a transaction. Blocks and transactions. Okay. Bunch of transactions from word state sigma t plus 1. Okay. A bit bigger. Transactions are collected into blocks. A block is a package of data in the form of transactions. Chain of states. Okay. If you focus on how the global singleton word state of Ethereum changes after each block, Ethereum can be seen as a chain of states. Blocks packed with transactions are the ultimate state changers to the Ethereum word state. Focusing purely on the blocks, Ethereum can then also be seen as a chain of block or a blockchain. This is one of my definitions in one of them short videos. Stack of transactions. Okay. Genesis block. If you ignore the block-based view and focus purely on a ledger view, just focusing on the number, Ethereum can then be seen as just a collected stack of transactions. Each transaction subsequently changes state, and so the state changers are simply stacked. Refresher on the Ethereum world state. Ethereum can be viewed as a chain of states. There is only ever one single world state, and that world state is changed by blocks packed full of data in the form of transactions. Okay. This is super long. I don't know. I should take a break here. It's too long. I could have been like 2 or 3 lessons. It's okay. 40% Ethereum. 40%. Basically, it's a lot of theory. There is a lot of theory. Several views of Ethereum world state. The Ethereum world state can be seen from several perspectives, all just different conceptual vehicles. Choose the one that best fits your conceptual understanding. Mapping view, table view, object view. As seen above, the Ethereum world state can be seen as a mapping, table or an object. It is the ultimate source of all Ethereum state, including balances and smart contracts code plus state. Accounts are simply ledger entries that are indexed by a public address into the world state. Query the world state by providing it an Ethereum address, and the world state will return the address account state, balance, nonce, smart contracts code, and state if applicable. Okay. Wait, so an account can be a smart contract? A smart I think no. Yes. An account... no. An account can be a smart contract. A smart contract is not necessarily an account. Okay. There are two types of accounts. POA contract account. This account does not have a private key. As seen in the diagram, this account contains 2 extra properties on its state: storage hash, code hash. Okay. Hey Dev, let's go on, Okay. Oh, I like this. No. Wow, 1 hour already passed. Okay, back to transactions. Why did we tangent into exploring the Ethereum world state and types of account on Ethereum? Well, because transactions directly affect the world state, and it's important to know what types of accounts are behind those transactions. Let's jump back into focusing specifically on transactions. A transaction is a single cryptographically signed instruction. It is a signal of intent from an owner of a private key that they want to change the Ethereum state. Reading data from Ethereum does not require an account. Right. This is super cool. Say something in the chat. I'm gonna take a screenshot. Ah. Come on. Oof. Word state. Two types of transactions in Ethereum. Two practical types of transaction. External actor, contract creation and message call. This is important, this part. Contract creation, special type of transaction. Message call, a transaction initiated by an externally owned account interacts with another externally owned account or a smart contract. This transaction does not create a new entry. It's basically a way of communicating. Okay, Ethereum transactions architecture. The above diagram shows all the properties that are packaged up within an Ethereum transactions. Okay, all the transactions field present above. Nodes, recipient, value, Y parity are S, okay. Init or data, gas limit, type, max priority fee per gas, max fee per gas, chain ID. Uh, 42, 40. 72, 12%. Months, so I'm almost at the half. Let me take this. Let me see if we can get some more people. I should prepare the message of the giveaway for the next times. Yes, 75 likes. Ugh. Okay, let's go. Okay, sorry, interruption. Okay, blockchain equal to blockchain equal to globally shared transaction database. Okay. Today I can't find a place to this microphone. No. Sorry, one moment. Okay. Transactions are so important that one can refer to blockchain as a globally shared transactional database. This is dangerous. It can be dangerous, it depends on what you do. Everyone keeps a copy of the latest Ethereum world state. Nice. Assigned JSON RPC. Tobiloba, let's go. 34 minutes, and I finished half of my 12 months of 12 hours live stream. 12-hour live stream. Let's go. If you want to support this crazy initiative, like the video, share the video, subscribe, make your friends subscribe, and let's go. The more I get traction, the more I'll do live streams. I'm doing more because I'm getting more traction. That's the only thing. Not asking for money. If you want to become a member, if you to make a donation, it's always welcome, but that's not the initial goal. Julia, should be publishing some Christmas pictures. What do you think, Julia? Okay. As the diagram above shows, you have 3 routes to interact with the Ethereum computer via a connection to an Ethereum node. Contract creation as an EOA. I can't really remember this. You deploy a new smart contract to the Ethereum computer via special transaction, message call, and inspection. Transaction object example. Okay. Nice. Auto manually construct call data. Once we send a transaction. Okay. Once we send a transaction that points to a smart contract, how does the contract know what specific function you intend to call? Well, all those specifics end up going in the data field of each transaction. Here's the algorithm to manually construct call data. Say Alice wants to call the withdraw ether function of a faucet smart contract. Alice must take the I don't know how to pronounce this word. Hash of the function signature. Okay. Take the first bytes, the function takes no argument. In the function took arguments, you would need to hash the entire function signature. Final call data construction. Oh. Conclusion. Phew, what a learning blast. The TLDR. It would have been better, to be honest. Transactions rule everything in Ethereum. They are the main changers of state, so we should know they're first-class citizens, which after today we do. Know them the architectural level. We are still at a low level at this point. We didn't write anything. We saw how to make read requests in the previous activity quite easily. We want to make you perform a signed request as an activity. Why? Because it's quite a long script to write. Trust us. We've gotten low level enough. We have just one more module left this week. Intro to Ethers.js. Tool like Ethers.js and Alchemy SDK abstract all the low level dealings we see here away from us, allowing us to focus on pure development. You'll see. We learned low levels so that we become competent Web3 developers. But we learn all the high level libraries meant to make us Web3 developers superstars, starting with Ethers.js, the Alchemy SDK. Okay, now that you've learned about JSON RPC, it's time to put all the knowledge to the test. In this lesson, you'll be crafting JSON RPC requests and sending them to a local Ethereum node written in JavaScript. You will be doing this by testing purposes. The JSON RPC parameters will be in the exact same format. You will need to use the Ethereum JSON RPC API docs. Okay. almost at I don't know. I don't know if I should finish it today. I don't know. Maybe no. It's too much. We have a lot of time. 29 minutes. Let's go. Current block number. The Ethereum blockchain adds a new block about every 12 seconds. We can also find the latest block number from an Ethereum node using its JSON RPC API. Okay, your goal, current block number. Let's make a JSON RPC call to an Ethereum node. We're going to use the send method on the provider. The provider we are using in this case is from Ganache Core. Update the get block number function to retrieve the current block number. The method we are going to use is called block number. Once you receive the response from the JSON RPC call, pull the result from the response. Pull the result. Return the result as the current block number. Let's see. Pa-pam. Okay, let's see. Result from the response. Cost equal await. I don't know, support provider. The send method. No, wait. No. Provider. Method not supported, okay. I tried. Do this faster. Okay, let's see. No, this is the method. One, update the get block function to retrieve the current block. There is not an example. Okay. This might be the last one. Let's try to use that's it. This is Ethers.js, Ganache. Interesting. And don't forget, Navilab, just have to decide when. Like this. No. Okay, let's read again. Let's read this. See if I find it. It's not here. Okay. Method not supported. For what? Wait. No, okay, I'm stupid. Okay, I'm stupid. I can't read. I'm a bit tired. There's also another arrow. Okay, I'm stupid. There was the arrow. Okay. Response result. Okay. Pull the result. Return. This done. Okay. Get balance. Every Ethereum address has an associated balance. You can see this balance if you go to Etherscan. Here's an example address. Your goal. Okay, now I can I can read. Okay. I'm a bit tired. Method. The method requires you to fill in two parameters, an address and a block number. An address. Get the balance for the address passed into our get balance function. Fill in the params. Come on, let's go. Last one. Last one, and then we wrap up. I'm a bit tired today. So, we're going to make another JSON call. Just okay. It's not clear which is the address. Is this one? Not clear. Wait, there's a lot. An address and a block number. Get the balance for the address. Ah, the address. Ah, in the I'm a bit tired. Yes. No. Let's go. Oof. Let's go, let's go, let's go. And then we should return let's see. Bam! Nice balance, dude. You successfully retrieved the balance from an Ethereum node. Awesome. Let's ride this wave into the next stage. Maybe stop. I mean, this is not very hard. When sending a transaction in Ethereum, it's a requirement to include unknowns. The reason is quite simple. You don't want your transaction to be sent twice or more than that. How could it happen? Let's say, okay. This account nonce is simply a counter for all the transactions. Every time you send transaction from your account, the counter goes up by 1. Easy. Now we need to find the appropriate method. Okay. Let's see if let's see if ChatGPT oh, let's try. Let's see if ChatGPT is doing, is helping. At get transaction count with the address. ChatGPT can be useful. Let's see. Let's try. Address, let's say like before. Ah, we have to return it. Response. Okay, let's go. Bam! Why did the transaction fail? Because it was a nonsense. Okay. After this, we can stop coding for today. I think Vito is in charge of doing this. Enough. That's it. 15 minutes. Thank you. Nice. Okay. 10 minutes. Enough. Closing in 10 minutes. ChatGPT is useful. It's useful because you can ask stuff. It's an alternative. Okay, so okay, now in 2-3 minutes I'll give my final thoughts on this first part of the Alchemy University. So let's focus and then we celebrate and we're done. It would be nice to reach 100 likes. That's it. What should I do? What else do I? With Twitter. Okay. I think I removed the music. Okay, so before I give you the final thoughts on the Alchemy University, first of all, let's stop the music for a while. Let me put this in the right position. So last call, giveaway, you share the live stream's link, you tag me, and at the end of the live stream I'll select a winner for a Udemy course. So if you want, this is the last opportunity, okay? And in 2 minutes we will make the final thoughts. Okay. Nice. Okay, can you hear me? Let's put this. Let's put this a bit bigger. I'll also start recording. 15 people. Nice. Let's start recording. Okay. So, full mode. Alchemy University. Okay. So, okay, so which are my thoughts about the Ethereum University tutorial so far? These are hot impressions. So the first impression is that it's very heavy, you can say. So it's probably I would not recommend this for beginners, but maybe it's because I'm doing this in a rush, we can say. So if you want to take it easy and you have a lot of time, it can be a good decision. There are some things in the tutorial that I don't like. First of all, I don't like that there is no dark mode. There is you can't do Control Z. You can't like reset a challenge. Like if you mess up your code, I don't know, you should go on Discord. And then thank you for subscribing. So so this is something that I don't like much. Another something that also I don't